energy E. So again, you can see that the typical values of local density of state and scattering rate, they become vanishingly small first for the states on the edge of the spectrum, and a much stronger disorder is required to make them small for many body states in the middle of the spectrum. So in this way, we think that local density of state and scattering rate can also carry signature of many body mobility edges. So this is the last set of results. So far I have shown you results for, or maybe I will skip this thing because in interest of time, just to take questions. So this is just one last slide I would like to show. So we looked at the scattering rates as a function of effective interaction, and interestingly, the ratio of the typical value of the scattering rate and the density of state is almost quadratic for the nearest neighbor interactions, and even for higher range of power law interactions, it is very close to the quadratic form. So this shows that any many body theory which is able to treat the interactions up to second order should be able to capture the effect of many body localization, as long as one is looking at eigenvalue resolved Green's functions or infinite temperature Green's function. So with this, I will conclude, and thank you for your attention.
Thank you, Aarti. So the talk is now open for questions. Manas?
Hi. I had a question about, so in the infinite temperature limit, you get effectively the weighted spectral form factor, right?
Yes.
But if you compute it your way, do you actually see a ramp, the random matrix theory ramp, on the ergodic side?
So actually, we never looked at the Green's function as a function of time. We always do the Fourier transform and looked at the spectrum in the frequency space, because that is what generally experimentalists do.
Right.
But we can look at it as a function of time. Actually, only after listening to your talk this time, I realized that the spectral form factor is actually kind of hidden in the Green's function.
Oh, okay. Yeah, that will be interesting. Yeah.
So what the reason I pointed it out is maybe using the analytical expressions you have, one can try to get some upper bounds on the Green's infinite temperature Green's function and the local density of state from there.
Yes. And also on the ergodic side, you should be able to see the random matrix theory ramp, right? That also
yes. So we can look at the Green's function in time space. So by default, we were looking at it in frequency space. That's why we missed out that part.
Okay. Thanks.
Yeah.
Arnab?
Yeah. Aarti, so if I understood correctly, the intuition behind this many body Green's function was that if you sort of take an exact eigenstate in the MBL side and you hit it with a local operator, the excitation still stays localized, right?
Yes.
Okay. So when you do numerics, of course, you look at sort of all the eigenstates and then you see these typical features and all. So in your numerics, did you see like a sort of a very small number of eigenstates in which, even in the MBL side, in which the excitations were delocalized? Because somehow that is supposed to happen, but that number is vanishingly small. So I'm just wondering with your system.
No, I didn't understand the question. Sorry.
Okay, so the question is, even in the MBL side, there are a set of high energy states which are measure zero, but the number is large, in which if you create a local excitation, that excitation actually spreads throughout phase.
So, so if you look at this figure, can you see this figure? So are you talking about the states
No, I'm not talking about the mobility edge or anything. Let us go to a MBL where, okay, so if you look at this Imbri paper and there are some other subsequent papers, so even in the MBL without any mobility edge, there are sort of a set of measure zero states, but of course measure zero when you normalize with the entire Hilbert space. Okay? In which if you sort of create an excitation on top of a exact eigenstate, that excitation spreads in space. You see, so because you're looking at this, I was just wondering if you look at your entire data files and all, do you see signatures like that? Of
No,
course, they're measure zero. So
these long tails which you are seeing, right? At large values of local density of states and scattering rates, they actually correspond to the kind of rare events you are talking about, right? So for example, here, you see the tail is long. Even for W equal to 8, although because the weight at 0 has become very large, right? But it's not that the weight is exactly 0 at other values of the local density of state.
I see. So maybe I'll talk to you later to understand this more. Thanks.
Yeah.
Okay, so we have time for just one quick question. Soumya?
Yeah, Aarti, thank you for the nice talk. So one small thing. So in the limit of single energy state, isn't local density of states and the IPR will be exactly same? Because that's how the multifactoriality also.
Sorry, it's the local density of state?
And the IPR, you said that the exponent does
Yes,
not
that's what I told, right? That in the single particle case, sorry, I'm just going to that slide. So in case of single particle localization, the IPR is basically related to the local density of state. And that's why the scaling exponents are also related. So it is not surprising that their local density of state acts as an order parameter.
Yeah.
But we don't have any such simple relation when we introduce the interactions in the system.
No, but it's
Between
also
the
about the
IPR and the local density of state. But still local density of state acts as an order parameter there. Is that what you were asking, or?
Yeah, I was thinking that the definitions are same, right? So you are essentially broadening the delta function when you calculate the local density of states. The question I'm saying that if I take that broadening to 0 in the limit system size goes to 0, infinity, wouldn't it be exactly same, means even in the many body case?
No. How can it be the same, right? Because see, now here in the single particle thing, this is a single particle wave function in real space.
No, I'm talking many body wave function in Fox
I suppose you guys can discuss maybe later, because I think it's going into more discussion mode. So let's thank Aarti for a very nice talk, and we'll move on to the next talk of the session, which is by Soumya actually. So Soumya Bera is the next.
Stop sharing. Shall I just leave?
Please, yes. Stop sharing. Yeah. Great. So Soumya, over to you, and so 25 minutes in all.
Yeah.
So I'll let you know after 20 minutes are gone. Yeah.
Sure. You can see my screen, right?
Yes.
Okay. Thank you. So again, good morning, everyone. I would like to also thank all the organizers for this meeting and inviting me for so many years now. I also would like to thank Aarti for giving a very nice introduction on the many body localization. So therefore, I will skip it. Actually, I'm going to skip my entire talk, and I'm going to talk about a different thing. Yeah, and I would like to be brave and want to talk about something very different today. So I will be talking about the fate of MBL today, actually, and I will give a brief review of what MBL is and where the field stands, at least according to me. Okay, so whatever Aarti says about MBL is going to be in the talk, so please ignore the repetition. So at the very outset, I would like to tell you what at least I feel is the scenario. Yeah, so usually we think about a generic system in the case of MBL. By generic system, I mean I have an interaction in the system in one dimension, mostly in density interaction or spin interaction, nearest neighbor. And I have disorder, on-site disorder, and something is distributed between minus W to plus W. So that's what exactly the model that Aarti showed. I have this in mind. So this is a kind of a picture that already we believe is there. So this line that you see here is the strength of the disorder. Right now, what I have taken is that the strength of the interaction is exactly equal to half of the hopping amplitude. In that language, the critical disorder strength, which actually turned out in 2015 or so, was around 3.5. Okay, so interaction 1. So in the XXZ language, if you take a spin half XXZ model, so we are in the XX point, and disorder is distributed between minus W to plus W. In that language, the critical disorder strength was believed to be around 3.5. In last 5 to 6 years, it has increased. It has increased significantly, and currently my understanding is that this interaction disorder strength is around 5 and can be even more. Okay, so it's a factor, almost by a factor of 2 increase. The system size, by the way, has not increased by a factor of 2 yet. Okay, so what we know? So what we know from the dynamical point of view is the following. So in the very weak, let's say, disorder strength, we have an ergodic phase. By ergodic, we mean that ETH is holding, the wave functions are diffusive. So if you look at the dynamical quantities, this is going to be diffusive. And entanglement will have a volume law and so on. Deep in the localized phase, let's say W, when I'm talking about deep localized phase, I'm talking really, really large W. If there is MBL, then it should have wave functions are localized in the many-body Fock space. The conductivity will be 0, no transport. Entanglement entropy will have area law and so on. In between, we have something. So this something is again very dicey and we don't really know what is going on. For instance, left of the critical point, we have again an ergodic phase, but the dynamics will be subdiffusive. Okay. By subdiffusive, I mean the following. I will become more quantitative in a few slides, but the idea is that if you calculate density correlator, so essentially current correlator, which is essentially the Kubo formula, then you will find that the charge will propagate subdiffusive. Okay. Now, where the boundary is between diffusion and subdiffusion is also changing over the year. So initially it was 1.5 or so. Now it has changed to 3 or so. So again, we don't know. And in the right-hand side, again, there is something happening. So it's not really exactly localized. So there will be a slow dynamics. There is a structure in the many-body Fock space, which we call fractal structure. I will explain again what do I mean by slow dynamics and what it is all about. Now this figure emerges because of the y-axis. Yeah. So what is the y-axis? The y-axis is my 1 over L. So I have a system size dependence in all of these things, right? And that's the reason why everything is not equal and everything is kind of uncertain. Given the nature of the many-body Hilbert space, so it's an exponentially large Hilbert space in system size, we are always very, very far away from the critical point. So we are over here. Yeah, so that is always the case, right? So we do have a critical phase. Even in a single particle, let's say a quantum phase transition, we will be always over there. But then we have this very interesting thing in our hand, which is finite size scaling. So we do finite size scaling and we predict where the critical point is and so on. So we may ask why it is not working here. So why the finite size scaling is not so good here. The reason is very simple. We are not in the scaling regime. So whatever finite size scaling has been done in the MBL literature always predicts WC 3.5 or 3.25 or something like that. And if one sees the data carefully, one will see that we never have a single point where we can do the finite size scaling. Is always shifting with respect to system size. So we are really, really far away from the scaling regime. Therefore, doing or even trying to do a finite size scaling is futile, according to me. Good. So that's kind of where we are. And I believe that we are really far away. And therefore, what we see is a crossover. Haven't yet seen. That's the punchline. The MBL phase proper.
Show more clarification. So these gray regions that you're showing, would they therefore shrink as you increase your system size?
Yes.
Okay.
That's the prediction. I'm predicting. Yeah,
okay.
Everything will. Yeah. Thanks.
And show me more interruption. I'm sorry.
No worries.
What are the units exactly? I mean, what is W? What is the underlying model when you're writing these numbers for W?
I will come in 2 slides. I will come in 2 slides, but let me just tell you. So in the language of spin, so if you take a spin half system and an XXZ model plus a Z field, yeah, in that model you put XXX points, so delta equals to 1. So and the disorder is distributed between minus W to plus W.
Thank you.
So, Soumya,
yeah.
Which quantity you are using to decide whether system is diffusive, subdiffusive, that is also very important. So, because different dynamical quantities are not really very consistent.
Agree. And I will come more precisely which quantity I'm using. Yeah. Thank you, Bharti. Yeah. Good. So let me tell you just a brief idea about what MBL is, and then I will move on. So the idea is very simple, right? So we are in a Fock space. We have a system which is consisting of all the two-body term, which already have the hopping and the disorder, plus I have a four-body interaction. And then if you think about in the many-body Fock space, all these single particles are localized because you have a disorder, 1D system, Anderson localized. And this interaction matrix element is essentially giving you hopping between these different Slater determinants. And that was essentially a starting point of what happens in the interacting disorder system. Now, if you think naively, you would expect, okay, if I have a sufficiently large matrix element, which is bigger than the level spacing over there, I will have a large hopping amplitude in this one body problem, and I will delocalize. And this is initially was the thought, but then again, these two seminal papers told us that no, okay, there are regimes where I will get into the opposite scenario and I will see localization. But you see that the naive idea is that there is delocalization. That's one thing I want to mention. There's another way to think how the delocalization happens, yeah, and that is called avalanche scenario. So let's think about the following. So I will go through the argument very slowly. So stop me if you don't understand. So this is my 1D chain, yeah, and then this rate region, what you see is in the 1D chain, which is completely localized. Okay, so all these spins are localized to begin with. However, there are rare region effects. So in a generic system, you will find a block of spins which is delocalized, even in the completely localized system. And this red block is such a scenario. Okay, so this red thing is a delocalized spin in the midst of a localized spin. Now the idea is that if there is a delocalized or an ergodic bubble, so by ergodic again I mean the RMT is hold and the spectrum is completely Wigner-Dyson and things like that. There is a possibility that this region will increase over time. Okay, and let's also imagine that this red becomes yellow. So I have kind of the ergodic bubble kind of eaten up your sum of the spins. Okay, so right now this is the scenario. So I have a N0 spins to begin with, but then in the right hand side and in the left hand side, I have half N of the spins which is eaten up by the ergodic bubble. Now, given that situation, you can ask the following questions: what happens to the other part of the system? Will the ergodic bubble keep on extending, or it will just stop and the localization will survive? So that's the question we are asking. Now, as this is all the spins are localized, so the interaction between this ergodic bubble and the rest of the spin is exponentially small. Okay, so the matrix element between them are exponentially small, and that's where the argument comes. So the decay of a typical matrix element, if you just think about a simple golden rule type of explanation, so there is an exponentially suppressed matrix element divided by the dimension of the Hilbert space of the bubble, which is 2 plus N0 plus N. So this is N0 plus total thing is N, another N. And then this matrix element, we need to compare with the level spacing of the bubble. Okay, so the bubble level spacing is nothing but 2 to the power minus N0 plus N, plus the many body level spacing. Now, if you look at such a quantity, you can clearly see that if I go into a scenario where gamma, yeah, the matrix elements is much, much bigger than delta, I will be able to continue this eating up process because the matrix element is larger, the energy scale that is associated with the level spacing is smaller. So I will just win in some sense. And that essentially defined through this one characteristic length scale, which is called zeta. The zeta is essentially the decay of this matrix element. Okay, so there is a critical length scale, which is 1 over log 2, which comes from this log. If it is exceed that, you will always see delocalization or thermalization. And indeed, this is an idea that gives you a scenario from where a localization to a delocalization transition can happen. And in 1D, this is how people believe that the transition happens. In 2 dimension, just to mention, just in higher dimension, this condition always satisfies gamma greater than delta. And the prediction of this the Rock paper is that in 2 dimension, MBL is always unstable towards an inclusion of an ergodic bubble. Good. So that's kind of the scenario. So we have this picture that there is avalanche mechanism, and then there is all these finite set effects. How do we deal with all of this? But there are experiments as well, right? So we need to give credit to the experiments. Or before that, just to be more careful with my Hamiltonian, again, it's an XXZ model written in the Fermion language. I have a disorder which is distributed between minus W to W, and the interaction strength, which is density. And this is essentially the fast 2 paper, which tells you that the strict definition of MBL is that the conductivity goes to 0, and the conductivity in the delocalized phase at finite temperature will be goes to the true derivative. But okay, so we just forget about it. But let's look at the experiment. This already showed. So the idea of experiment is very simple. So you look at a cold atomic system over here. You have not a random disorder, but a quasi-periodic disorder. Doesn't matter, but you look at imbalance. And what you see that at finite disorder strength, the imbalance is flat. It doesn't go to 0. Yeah, and this flatness is what they call MBL. And I will tell you, and I will give you reason that this type of operator or this type of observable is a bogus thing. So one should not look at it ever. Okay. Second experiment, this is on an ion trap experiment. Again, you see similar type of Hamming distance here. And what you see here is that the Hamming distance, or again, if it goes to half, it's a delocalized. If it doesn't go to half, localized, and it tells you that, okay, there is something colloidal here. This is another experiment. This is another experiment, which is in the 2D system, again by the Immanuel Bloch group from Munich, doing the same thing. So you have a 2D cloud of atoms. And then over the time, you see whether, so this is non-interacting, this is interacting, and then distinguish between that picture versus that picture that is delocalized, that is localized. You decide yourself. That's the science. Good. So this is where we are. The question is, so therefore, what shall we look at? So what I will be more interested in is, as I said, is a density correlator. Okay, so this is a density at N0 at the 0th point, it can be middle of the system. And then over time evolution, you look at the Nx and T. In particular, the second moment of that correlator. Okay, so this is x squared phi xt, and then x, I subtract the mean value of it. So if you look at it, and I will be looking at mostly in the MBL phase, not in the ergodic phase. Okay, so if I look at that thing in the MBL phase, so by MBL, I mean the traditionally which values of W I will look at, which are in the MBL phase. What you see here, several curves. Let me go through it. So this is delta x of t as a function of time from 16 to 24 system size. And what you see, this dot line is a line where I turned off the interaction. Okay, so what it means that my non-interacting system is not increasing. So you can think of it as a wave function. The wave function is stuck. Okay, so that's your localization length of the non-interacting system. And now what you see up there is a scenario up to time scale that we can do, which is like 10 to the power 3 in the unit of the hopping. What you see is that with increasing system size, we see a growth of this delta x. Other way of saying that the charge correlator increases or the wave function propagates. And that keeps on happening at W7, at least again to the time scale that we can see. Now, definitely whether it saturates or not, we have no data to confirm, but let's say this is what we have. Right? Just to give you an idea about the experiment, the experimental time scale is of the order of 10 to 20, yeah, in the unit of hopping. Okay, now this lower panel is the Aubrey-Andre potential, which is done in the experiment. And what you see again, the similar type of feature that for large disorder values, we see creep dynamics. So the density correlator, the charge correlator keeps on increasing, at least with the increasing system size as well. Okay, so how to understand it more? So in order to understand more, let's understand what is the exponent that we are getting. So this is what we look at. So this is the beta of t, a running exponent. So this is, we don't fit anything. So we just look at the log derivative of this delta x with log of time, plotted as a function of not the time, but a proxy of time. So what we do is delta x divided by the single particle localization. So just remember the delta x was over there, single particle localization is defined over here. So we divide these two things and plot it in this x-axis. You may ask why so? The reason is that we want to see the physics of interaction, and that can be seen in terms of distance when the system exceeds the single particle localization, okay, not below that. Good. So whatever we have to look at beyond 1. And what you see here, so this is for this large disorder with increasing system size. So the arrow tells you that with increasing system size, these data points are increasing as well. Super slow, but it does. In particular, if you look at the largest system size, which is 28 here, we see a curvature. The question is whether this curvature develops and saturates such that the beta becomes finite. If beta becomes finite, it means that there is a slow propagation of charge. And this is the full distribution itself. And what you see over time that there is a code. So there are two length scales associated with this transition. Actually, at least in this correlator, one is that the core is completely frozen. So you see that there is no change in the core, but then there is a tail which keeps on coming up. And if it keeps on coming up, this is what it translates to. Now, you may say, okay, this is theory's dream. You cannot go to such a large system size, such a long time, and also you cannot really probe such a small exponent. That's not quite true. In experiment, this is an experiment done again in the gold atomic system that exponent has been probed. Okay, so this is exactly the same correlator with the similar alpha, and what you see, the same thing. So this is the transport distance as a function of time, and you see growth. So this is experimental data. So there is this growth, and they again, whatever they call MBL, whatever the value is, there is a growth. Okay, and the exponent has been plotted over here. So this is the exponent as a function of disorder strength, and you can see it. They did not see a zero exponent yet. Okay, so I have no idea why they call 4.8 being critical, but what you see that at this point the exponent is large, and again this is continuously going down and a finite exponent. At least from this observable, the system is still delocalized, or at least slowly thermalizing. Is this only experiment and is this our only data? That's not quite true. So there are even recent work. So this is work from essentially this year by Sirkar group as well as Kuba group from Poland. What they plot here or what they calculate here is what is called particle entropy. Okay, so what is particle entropy? So they calculate what is the probability of finding n particle in a bipartite system. So you divide the two systems, A and B. You calculate the probability of finding n particle in partition A, and you construct such an entropy out of it. And what they say is that if you increase the time as a function of, so just ignore their disorder value. So these are all large disorders, so somehow they have a factor of 5 somewhere. What you see here is that there is an increase, and this increase they claim log t, but again these are not really log t. It's a power of log. You can see that there are two crossing and so on and so forth, but nonetheless there is an increase, and this tells you. And if you do such an experiment in a localized system, this should not be the case. It should be a flat line. Okay, so in some sense, this is also hinting towards what the experiment sees, what we have seen. Good. So, is there a question?
Yeah, no, so I just wanted to point out that there's something peculiar with the experiment because what they claim to be thermal seems to have the flattest curve.
Yeah, here you mean. So the flattest curve is just because the time scale is just, so this is done for one system size only, and the time scale to reach that plateau is faster. Yeah? So that's the reason. So if you do another system size, this flatness will go up. So there will be a curve which will follow, and then the flattening will be up above there.
But so have they really checked it, or they just assumed it?
No, they
because
have
if you look at the long time scaling, the slope at the long time, then this looks flat, right? So
yeah.
One should claim that this is localized.
Actually, that's yeah. But you see also that they don't really plot the exponent beyond. But yeah, what I said is correct. They haven't checked it at least experimentally, but no, they have checked it even experimentally. 8, 10, and 12. Yeah, they did that. Okay, so how do we understand again all of these things? So this is our data. So you look at again the density correlator with the largest disorder that you can have. So this is the disorder strength 10, which is at least 2 times the critical disorder strength that people call about. This is distance I and ij. So the correlator has an exponential tail, which is again because this is sorry for the small numbers, but this is essentially the log scale. And you increase the time from 30 to 470. So you increase the time by a factor of 10. And if you look at the last point, it also, so this dashed line is 1 order of magnitude. The data point, the density correlation increases by a factor factor of 10 also here. So one order up with the time, one order increase. So again, what it tells you, at least the time scale that we have available within the system size that we have available, we do not see even for the largest disorder strength that the particles are localized. Good. So this is what
you have
sorry, it is
5 minutes.
NIT NG. Sorry.
Yeah, I just wanted to say that it's 5 minutes, including questions.
Right.
Yeah, Arti,
I will finish
you may ask the question.
Yeah. So this is quench experiment, Arti. So this is exactly what they do in the experiment. So you have an initial state, psi 0, which is a nil state, and then you calculate the density on that nil state. So this is disorder average and connected correlator. Sorry, I forgot to subtract the NIH. Yeah. Good. So what means, in a sense, that I'm kind of telling you that, okay, there is enough evidence to say that in the MBL there is a slow transport. So what to do? So the way I would say this is the positive message. So one should, first of all, this imbalance is a difficult quantity to look at, and I tell you why. So you look at the single density at a given point. You start with the null state, do a quench, and do look at the densities. Yeah. So if you look at, they are very, very big oscillations, okay, over time for a large disorder. I'll come back to this perturbation theory, but let me show you this imbalance. If you construct for a single sample this imbalance, you will wash out all these very high oscillations. That means you're essentially forgetting the resonances when you calculate the imbalance. Yeah, and this is the reason why imbalance is not a good quantity to look at. And as you know, that even imbalance cannot distinguish between an MBL and a non-interacting sample. So if you take an Anderson insulator and an MBL, imbalance cannot distinguish them. Okay, therefore, one has to be very, very careful while using that. Let me go back. I will just characterize these oscillations, and that's where I will end. So what I will do a simple perturbation theory, where my perturbation is essentially the hopping as well as the density-density interaction, and H0 is my disorder. If you do such a calculation, it's a very simple calculation. So this is an undergrad, so you can do that even. But you can show that the density, the single quantity density in the second order perturbation theory, 1 over tau 2, has two frequencies that is involved. Okay, so these two frequencies are given by the disorder at two different points. J and J plus 1 are the two different points, and D is the interaction strength. So what it means, so if you keep on doing the perturbation theory, you will keep on adding the frequencies. Okay, and all these frequencies are going to be important because these are the frequencies which are the resonances. If you do such a calculation and try to do the exact calculation as well and the perturbation theory, you will see that you can match very nicely the frequencies. But at the same time, you also see that there are deviation as we increase the time. Sure, as we increase the time, number of resonances will increase, number of frequencies that contribute to this sum will increase as well. So what it is, so what is happening? So this is my take. So we do have a Wigner-Dyson ETH volume law transport in the weakly disordered system. We do have all of these things over there. But the critical point is essentially the proliferation of frequencies. Okay, so what it means that my perturbation theory is never going to capture the MBL, that's for sure, because there will be enough resonances and enough frequencies that will I will not be able to do. But the critical point is even more dangerous in terms of perturbation theory and in terms of looking at it. So what it means is that there is infinitely many, sorry, not infinitely many, but there is a large number of frequencies associated in the MBL phase, and that number kind of diverges as we go close to the transition. And this is how I think of the MBL transition, and this is why I think that we have not yet seen the MBL phase proper. What we have seen is a kind of a very weakly, strongly disordered and interacting Anderson phase. Good, I will finish it here. So the main of the work is done by Saurabh Nundi, actually, who was a postdoc at IIT Bombay, now he moved for his second postdoc, and Ferdinand, who is so there are several funding agencies I would like to thank, and I would also like to thank you for your attention.
Thank you, Soumya. So questions, Aarti?
Yeah, Soumya, thanks for a very nice talk. So can you please go to this slide where you were showing this oscillation in NI2? No, just after this. Sorry, one slide after this. Yeah, so what is this Q here? What is this Q relation? What are you basically calculating?
This Q?
Right.
So this Q is nothing but the average of the initial state. Q just denote the null state, actually, nothing else.
So you start with the initial state.
We start with the, right. So I start with the size 0 initial state, and then I calculate what is the density at each point over time.
Okay. And just one comment about your statement that imbalance cannot distinguish between MBL and Anderson localization. See, that is true only if you are looking at the extremely localized phase, right? But if you look at the approach to the localized phase, then of course you can distinguish between MPL and higher order Anderson localization, I mean higher dimensional Anderson localization transition, because in one case, for the non-interacting, you will never see a power law decay. But for the interacting case, you will see a power law decay, and that exponent slowly goes to 0 as you approach the MBL transition, right? So isn't that a good way to distinguish between Anderson localization and MBL?
Yeah, so in the weakly disordered phase, yes. In the weakly disordered phase, yes. But this power law also changes over time and system size. That's the problem. The power law is not fixed. But your statement is correct.
The power law changes, but there is always a decay. I mean, it doesn't become flat initially after the initial spread.
No, but you see, this is a flat line. There is no decay in the large disorder.
No, that is very large. That's what I'm saying. So approach to the localization transition. So if you are in the sub-diffusive phase.
In the ergodic phase, I agree. But you see, this is not so large. 5 is where the critical point, or maybe even 6, but not that large.
Yeah. So I'm saying on the delocalized side of the transition point, you can see the difference between non-interacting and interacting.
Sure, I agree. Sure.
Okay, let's take another question. Sorin?
Yeah, so this is regarding the bubble you mentioned. So is there a way to, so is there a RG calculation which shows how this bubble grows? And then the first question is, are these due to quantum fluctuations? Can you estimate their size, what it should be, typical size in a given system?
Right. Excellent question, Shovin. Excellent question, Shovin. So the idea is that you cannot do microscopic calculation with this. Yeah. So you can do this type of simple arguments, qualitative arguments, but in order to do based on this idea, what I explained, people have done RG, but these are qualitative phenomenological RG. So they assume that there are bubbles already in the MBL phase, and they take a particular distribution of them, and then they derive some rules. Yeah. So that, for instance, let's say ergodic bubble, if it is in between a localized phase, another ergodic bubble, there is some rule, and so on and so forth. You do this phenomenological RG, you get something out of it. Nobody could test it because their always claim is that they obey, for instance, the exponent. We get whatever exponent we get in 1D is around 1. So localization length exponent or some exponent in 1. RG suggests that it should be around 3. We could not test. So things like that. So they say that, okay, 10,000 system sizes needed to do that. We can do a detail. So I don't know. There are RG. RG also suggests that the MBL transition is a costless, Thouless transition.
I see.
Okay, we'll take last question. Arnab?
Thanks.
Yeah, so Shomo, so I guess your point is that the omega critical is much larger than what people claim routinely. And I guess that's what you were showing in through these creep dynamics and stuff.
Right.
So in your numerics, can you show a plot where you have sufficiently big W and you can therefore claim that there is a pristine MBL by whatever?
Yes.
So maybe I missed that. Yeah.
No, it's not. I haven't shown it, but I will show it. So when I write this W star, you see, so that's what I think is an MBL proper. Yeah, so that's where the MBL happens. But this is very difficult to capture. So what you have to do and look at something more rather than just density, just imbalance, or just density. What you have to look at, let me go back, is something called fluctuations. Okay, so you have to look at the time fluctuation because that's a much more easier quantity to look, easier to, I would say, find an experiment because, and if you do that, that will give you a W star. So I don't, this is a separate talk. That's the first title of my talk actually, but, and then you have to look at this exponent. This exponent actually, how they decay is much less system size, means it has a system size dependence and everything, but at some point of time, this exponent exactly goes to 0.
So is this analysis on the archive?
some part of it is there, some part will come out.
Okay,
Yeah.
I see.
Okay.
Okay, let's thank Soumya for a very nice talk.
Thank you.
And let's move on to the next talk of the session, the last of this session. This is by Yasir Iqbal from IIT Chennai, IIT Madras. Yasir, you may share your screen, please.
Yeah, hello, good morning. Yes, do you see my screen now?
Yes, yes.
Okay, let me make it full screen, I guess. That'll be better.
Yeah, great.
Okay.
So I'll let you know when 20 minutes are over.
Sure, perfect. Yeah, thanks so much. Yeah, so thank you to all the organizers for giving me the opportunity here, and also for the previous years. It's really a pleasure to be part of this meeting. So what I'm going to talk about is a recent work of ours on the never-ending saga of the Kagome lattice. Primarily, its interest is driven due to the fact that it's now more or less well established that there is a quantum spin liquid ground state of the Heisenberg antiferromagnet for small values of spin, in particular for spin 1/2. One of the key drivers of this understanding the physics on 2D Heisenberg antiferromagnets is given by variational approaches, in particular employing slave particle approaches and supplementing them by Gutzwiller projection. So in this work, I'm going to describe what has been the achievements and what are the shortfalls, pitfalls of this approach using Gutzwiller projected states for the J1, J2 Heisenberg model and the Kagome lattice. So this work recently appeared in Physical Review B. It's a collaboration with the postdoc Francesco Ferrari and Didier Poelblanc, Alberto, and Federico Becca, and my student Aishwarya Chauhan. So over the years, there's been now mounting evidence actually that the ground state of the spin 1/2 Heisenberg antiferromagnet and the Kagome lattice is a quantum spin liquid, and more so. We are now converging on the scenario that it's actually a gapless spin liquid. So there were, this has been sort of, there's been a consensus from different state-of-the-art numerical quantum many-body approaches. In particular, variational Monte Carlo was one of the first to claim for this scenario for Dirac spin liquid as the ground state. This was later sort of corroborated very strongly by a state-of-the-art density matrix renormalization group study done by Yin-Chen He and Mike Zalatel, Masaki Yoshikawa, and Frank Bohlman, and appeared in this paper PhysRevX, where they used the idea of flux threading to try to pin down the momenta of the Dirac cones using special boundary conditions. Around the same time, there was also a high-end tensor network study from the group of Tao Jiang in Beijing, claiming for a gapless spin liquid in the spin 1/2 Heisenberg antiferromagnet. Around the same time, there were also another study employing entanglement signatures and seeing what will be the signatures of emergent Dirac fermions in a Kagome spin liquid. So it's actually nice to see that all the doubts still remain here and there, but more or less, let's say we are converging to this picture of a U1 Dirac spin liquid ground state of a Heisenberg antiferromagnet. So this immediately triggers the question: how good is the stability of this state under various perturbations, especially given the fact that it's a gapless spin liquid, in particular with Dirac cones, and the question of the stability is a very pretty delicate one. And this is what we set out, addressing in this paper, in particular under the perturbation of further neighbor Heisenberg couplings. So the second nearest neighbor Heisenberg couplings, J2. So let me first flash the results before I delve into the details. So what we found is that this gapless spin liquid is actually quite stable within a finite window of parameter space until the introduction of a J2 coupling. So this is the phase diagram that one obtains. Here I plot the magnetization on the vertical axis as a function of J2 over J1. And you have the yellow dots, which shows the region where the Dirac spin liquid is found to be actually variationally stable. And then under a certain critical coupling, when you reach around 10% of J2 on the antiferromagnetic side, there's a transition into the well-known Q equals 0, 120 degree order. Whereas on the ferromagnetic side, it's a transition into a square root 3 cross square root 3 order. So there were a few questions which had not been answered so far. One was, what is the nature of the phase transition? Is it first order? Is it second order? There were some insights from field theory, but not much from microscopic numerics. So this is one of the questions that we addressed in this work. And the second was that also the estimation of the phase boundaries, where they precisely lie, was not so well in agreement. There were varying estimates ranging from few percent to about few tens of percent of J1 coupling. And the question was that, is it actually true that the Dirac spin liquid remains essentially stable in this entire region of non-magnetic behavior? Does it give way to other kinds of states like Z2 gap spin liquids or valence bond solids, pneumatic spin liquids, other kinds of competing variational states in the low energy manifold? So the main result was that, as I said, there's a finite region of stability of the gapless Dirac spin liquid. Miraculously, the accuracy of the variational gapless state improves upon the inclusion of an antiferromagnetic J2 coupling. So this is something that we revealed. We also showed that the situation when you introduce a ferromagnetic J2 is actually quite problematic. Though variationally the Dirac state remains stable, it no longer represents an accurate description of the ground state. And finally, the transition on either side is first order. In particular, the transition from the Dirac spin liquid to Q equals 0 is first order, although from symmetry arguments, it's actually permitted to be second order. So I'll go into this in a little more detail. And this picture has been obtained by doing variational Monte Carlo calculations from highly versatile Gutzwiller projected Jastrow wave functions. So let me now go. So the variational wave function description is rather quite traditional and quite simple. It just employs the decomposition of the physical spin operators in terms of abricus of pseudo-fermions, which are called spin-ons. So they are represented by these C operators. And the spin-ons are basically spin 1/2 and charge neutral objects in which, in whose bilinear combinations you write the physical spin operator and you preserve the spin algebra. The only problem that happens is that you actually enlarge the Hilbert space to include unphysical states which are doubly occupied or are empty. So the moment you plug this representation per spins in the Heisenberg Hamiltonian, you land up with a 4 fermion interaction, and you need to do a mean field decoupling. And the simplest mean field decoupling you do is in the hopping channel, although there is also a decoupling into the pairing channel that one can do, but so far I'll just restrict myself to the hopping. And since this formalism is SU2 symmetric and there's no way you can capture long-range magnetic order, the way to do that is to introduce a Zeeman field, which basically couples to the spins, and the presence of the Zeeman field in the thermodynamic limit then reveals to you whether there is magnetic order or not. If it is finite in the thermodynamic limit, there is long-range magnetic order, and if it's not, then there is none. And this is intimately connected to the magnetization. This is intimately connected to the presence of a staggered magnetization. So, so there are two things that one must do essentially in order to get a bona fide variational state for the spin model is to do Gutzwiller projection onto the subspace of 1 fermion per site, which is the original Hilbert space of the Heisenberg model. Right? And the second thing is that one must supplement by a Jastrow factor, which basically introduces transverse fluctuations on top of your classical XY state. And therefore, this is actually the key ingredient which leads to generation of long-range magnetic order, where these U's are the pseudo-potentials which are optimized within the Monte Carlo scheme. So your legitimate variational wave function is then defined as the mean field ground state of this quadratic Hamiltonian, then acted upon by the Gutzwiller projection, a projection onto the subspace of SZ equals to 0, and the Jastrow factor. Now, this is a strongly correlated state, and there's not much you can do with it analytically. So in order to evaluate expectation values, for this variational state, you have to perform a quantum Monte Carlo sampling. And fortunately, it's possible to enforce this projection exactly numerically in the Monte Carlo sampling. And therefore, the great thing about the approach is that you are really working in the correct physical Hilbert space, and your particle number is strictly 1 fermion per site. This, in the language of Xiaogang Wen, you could say that you are incorporating the temporal components of the gauge field exactly. Okay. And for the optimization of the variational parameters, we make use of a sophisticated implementation of the stochastic reconfiguration technique, which is basically a glorified version of the method of steepest descent. Based on this, one could actually...
Yasser, quick question. So, so when you talk about the variational parameters, do you restrict their number using further symmetries or something, or how do you go about it?
Okay, very good. So the thing is that the question arises, what should be the form of this hopping ansatz? And this is determined by symmetry using the approach of projective symmetry groups, which allows you to enumerate completely systematically all possible variational ansatz with a given symmetry. So if you want to classify, say, chiral spin liquids or fully symmetric spin liquids in a particular low energy gauge sector, say U1 or Z2. So given lattice point group symmetries and given the low energy gauge group, one is able to basically classify all possible. So it's good that you raised this. So let me just add to this that the best variational state for the Heisenberg antiferromagnet is found by a choice of hoppings, which are uniform in magnitude. So they're translationally invariant, but their sign structure is such which gives rise to a zero flux through the triangles and a pi flux through hexagons. And this is what is labeled as a Dirac spin liquid. Okay. So from now on, I will choose such a sign structure of hopping, which give rise to these fluxes, which is the only gauge invariant quantity. Okay, so this is the lowest variational, the best variational state that one can construct. This is basically captures the spin periodicity pattern. You can set it to the Q equals 0 state or the square root 3 state, and this is the Zeeman field. So
Yasser, another quick clarification. So when you enlarge the Hilbert space, there is a local constraint that is there, and so this projector makes sure that the local constraint is implemented, right? Or
that's right. Yes, it's implemented.
So
exactly.
Many methods, right? Many methods implement the constraint on the average. Some of these,
but this implements it actually exactly because you can do it in Monte Carlo sampling.
Right.
You can't do it analytically.
Yeah.
But in Monte Carlo sampling, you can actually just enforce this constraint numerically exactly.
Great, thank you.
So so this is taken care of absolutely properly. There are no deviations allowed from it at all. So yes, you're right. In many other approaches, this is sort of the shortfall, the shortcoming that they face. So what one can compute actually very easily from this is the square of the magnetization, simply by evaluating the expectation value, of the spin-spin correlation function, the equal time spin-spin correlation function. And in the limit that the distance between the spins goes to infinity, we know from the factorization property that this is simply the sublattice magnetization. So this is straightforwardly computed in Monte Carlo. And if you look at how this behaves, so starting from the nearest neighbor model here, you see that in 1 over L, the magnetization basically goes to the, so this is ultimately connected to the local Zeeman field. So they are equivalent. So here I show the scaling of the local Zeeman field, which on any finite system is finite. But then if you do a size scaling in 1 over the linear system size, it cleanly goes to 0, right? And it goes to 0 starting from the nearest neighbor model and adding, a perturbation of 2%, 4%, 6%, 8%, 10, and then you find suddenly a jump. You see that it no longer goes to 0, but rather cleanly scales to a finite value, right? Indicating that there is now long range, magnetic order in the thermodynamic limit. The same behavior is reflected actually in the magnetization here, which is the quantity I just described, where when you are in the spin liquid regime, it basically just clearly goes to 0, and then it undergoes a sudden jump, and starting from around 0.12, you see that it basically scales to a finite value and keeps on increasing as you go deeper into the magnetic phase. So this is on the antiferromagnetic side. You can actually compute the same on the ferromagnetic side. When a J2 coupling, which is a ferromagnetic nature, is introduced, and you see the same, that around 3 to 5% coupling, the size scaling actually shows you that that there is no long range magnetic order. But then suddenly there seems to be a phase transition where the system then enters into a long range magnetically ordered state. So the transition points on either side are that around 0.1 J1 on the antiferromagnetic side and around minus 0.06. So this actually site had not been investigated almost at all. And there were estimates ranging from 0.5 to almost 0.02. And the variational approach then tells you that gives its own estimate where the transition should lie into the ordered state. So there is an appreciable window of quantum spin liquid behavior, it seems, ranging from 0.1 on the antiferromagnetic side to minus 0.06 on the ferromagnetic side. So this is one thing. Now the second approach is that how does this estimate compare to actually the other estimates given by other approaches? So here I put a table from our paper where you see that in the presence of an antiferromagnetic J2, the estimate, as I said, from our variational approach is 0.11. There have been previous approaches using the bosonic, quasi-particles, Schwinger bosons, which give you an estimate which is good within few error bars. DMRG has difficulties in doing size scaling, because they're restricted to very few cylinder widths. But nonetheless, they also provide you an estimate which is not too far away. They predict around 20% of J1, you should see a phase transition. Tensor network seems to be biased a bit more towards magnetically ordered state and predict the region of stability to be a bit smaller. Exact diagonalization, of course, we all know that despite being exact, the problem is just the fact that they're restricted to rather small system sizes. Coupled cluster method seems to give the best agreement with variational Monte Carlo. And a one loop FRG has its own shortcomings. So it seems that there is some broad consensus that there should be a phase transition from around 10% to 20% of J1. On the ferromagnetic side, when you go into the square root 3 magnetic order, let's say the picture seems to be in a more narrow region, the methods agreed. So DMRG gives you around minus 0.1, and coupled cluster again seems to be in very good agreement with VMC. Let's say there is some reasonable window within which different methods are now predicting the transition, and our estimate lies pretty much within that thing. So now the question is that how do you ascertain what is the order of the phase transition? So let's first look what is known from field theoretical approaches. So recently there was a paper from the group of Ashwin Vishwanath unifying different orders on the Kagome lattice, where they worked out the quantum numbers of the different mass terms and the monopole fields, and found that the singular response of the Dirac spin liquid is actually located at the positions where one would expect a signal for the Q equals 0 order in neutron scattering, right? Which are basically the center of the sides of the extended Brillouin zone, and therefore a natural transition from the Dirac spin liquid to the Q equals 0 order, a continuous transition, is actually therefore expected. Okay. So this is what sort of briefly the field theory picture permits you, to have this kind of a continuous transition. And therefore we set out trying to ascertain its nature within a microscopic calculation, right? So, and this is most simply done by taking the approach which we all learned from Ashcroft and Merman, is how many minima should there be in the energy landscape as a function of the external field. So you can plot the energy of the variational state as a function of the local Zeeman field that you apply. And you see that inside the spin liquid phase, very close to the transition, when you're just approaching the transition, there are actually two minimas, okay? There are two minimas in the energy. And when you increase the system size, you see that the two minimas are actually stable, that it's not that, one is disappearing or anything like that. So we did calculations on 12 times 12 times 3, 16 times 16 times 3 in the unit cell, 3 sites. So we went up to pretty large system sizes, nearing around 2,000 sites. And we see that the two features of this energy landscape remain very robust. One is the presence of these two minima and the presence of a barrier between the two, okay? And this indicates, and then when you go on to the other side, when you switch over to the magnetically ordered side, just into it, at J2 over J1 being 0.1, you see that again, there are two minimas, which are well separated by a barrier, and the minimas as a function of system size remain robust, but the two minima switch, right? So what was the minima, which was at small field and ultimately size scaling to 0, basically, and was the global minima, and the minima at the finite field, which was the higher one, they have just switched their role. The one at the finite field is now lower, and the one at small field is now higher. So this presence of two minimas and their switching across a transition is the most clear signature that one can see of a first order phase transition. So this is something that we sort of address for the first time, that the transition, although being permitted to be second order, actually turns out to be first order from the Dirac spin liquid to the Q equals 0 phase. Right? On the ferromagnetic side, the situation is actually more direct. One observes that when you go from the Dirac spin liquid to the to the square root 3 magnetically ordered phase, the variational ansatz that actually gives you the lowest energy actually changes. It changes from, in order to correctly capture the square root 3 magnetic order, here you must not use the Dirac hopping ansatz, but an ansatz of a different kind of a U1 spin liquid, which has a different pattern of fluxes, right? So the solution itself changes, and that's a clear indication that there are two different solutions which are crossing each other, and you can carry one into the other, right? So that's clearly first order. And also from field theory, there is no reason, because there is no singular signature of the Dirac spin liquid at the corner points of the Brillouin zone, which is where the peaks of the square root 3 magnetic order would be expected. So there the transition is also expected from symmetry arguments to be first order, okay? But not so for the antiferromagnetic side, and that's why we set out resolving that and found indications of first order. So this is sort of how the energy landscape goes. I mean, you have a Dirac spin liquid here, shown by the blue curve, which is the lowest variational solution. And then you have basically a long-range magnetic order setting in, shown by the pink curve, and the energy intersection then gives you the answer. And on the ferromagnetic side, you see that there is a square root 3 order, which comes down like a cannonball, this green straight line, and basically cuts you here, and that basically ends the region of stability of the Dirac spin liquid, which is in the red line. I want to also mention you that in the previous works of ours, and also from some DMRG studies, there were claims of having a valence bond solid phase. And although we investigated this and we found how it competes with these other states, if a valence bond solid exists on the ferromagnetic side, it should be in a very tiny sliver of parameter space, almost vanishing. So it's almost very difficult to ascertain whether it will be a stable phase in any finite region of parameter space. So there was not a paper, but an APS actually talked by Steve White's student way back, which claimed this. And also we found before that also a valence bond solid, but one is not sure whether it will actually be there very close to the transition.
Yeah, so we have 5 minutes, including questions.
Sure. Okay. Yeah. So another interesting result we computed was that what is the overlap between the U1 Dirac state and the exact ground state on 36 side, employing exact diagonalization. So in this curve, we show the overlap of this symmetrized Dirac state with a few exact eigenstates computed by the Lanchos technique. And you see for the nearest neighbor point, as you go on the antiferromagnetic side, so the color and the size of the circle both denote the overlap. So the overlap remains rather finite, right? And it sort of slowly then starts going down. On the ferromagnetic side, you see immediately. So on the vertical axis, you have the ground state here, and then it shows the gap to the few exact eigenstates. So you see that the ground state, the overlap of the Dirac actually just suddenly collapses. So it goes from being around 80 to 90% to suddenly being around 6%. So that clearly tells you that the moment you introduce a ferromagnetic J2 coupling, the Dirac no longer represents an accurate ground state of the model, at least on 36 sites, right? And what happens is that the Dirac starts developing actually a good overlap with some exact excited eigenstates of the model, but no longer the ground state. So it's clearly that something happens the moment you introduce a ferromagnetic J2 coupling, and some other state should take over. But what we were unable to do is to actually try to find out what this new state is that sets in this region on the ferro side before square root 3 order begins. But something must happen. Now, how these results carry over to the thermodynamic limit, nobody knows. I mean, whether this is actually present there, but okay, this is so far what we can get on 36 sites, right? And this has to do with the presence of avoided level crossings in the ED spectrum, okay? And the same results for 12 sites are shown in the inset. So in order to show the accuracy of the Dirac state, a very good approach is to do the Lanchos technique. So the Lanchos technique simply consists in applying powers of the Hamiltonian and on a certain given trial state, And if this trial state is not orthogonal to the true ground state, you will ultimately converge to the true ground state under the application of some n number of Lanchar steps. So ideally, n goes to infinity, right? So here what we do is that we take, for example, the nearest neighbor model, and we start with the Dirac spin liquid, the variational Dirac spin liquid obtained by diagonalizing a tight binding, the mean field Hamiltonian with the flux pattern I showed you, and doing Gutzwiller projection. Simple as that. And then you apply some n number of Lanchar steps, and you plot it as a function of the variance. Now we know that for an exact eigenstate, in particular for the ground state, the variance should be 0. So when you apply the Lanchar step, you will actually decrease the energy and you will start converging to a 0 variance solution, which will be the ground state. So here I plot energy versus the variance, and you see that the convergence is actually quite smooth, except for a little non-monotonic behavior close to when you approach the ground state and you basically, reach the ground state energy. Now, the principle is that if you have a very good starting point, then your convergence must be smooth and linear. So if I take only the first 3 points here, so I start from the bare variational state, I apply one Lanchar step, I apply another Lanchar step, and I try to do an extrapolation. I actually land up with an estimate of energy which is not far from the true ground state here, obtained by applying some, say, 100 Lanchar steps, or the exact energy. Now, this tells you that the Dirac state already represents a very good variational description of the exact ground state. Now, the moment you introduce a finite antiferromagnetic coupling, say 5%, this convergence becomes even better. You get rid of this non-monotonic behavior and you essentially converge linearly and smoothly. So if I were not to do even Lanchar steps further, but just do 2 Lanchar steps, so the original state 1 and 2 Lanchar steps, and I extrapolate, I essentially hit the exact energy, right? So this becomes essentially linear, even better than what was there. So this gives you very solid evidence that the accuracy of the Dirac state improves upon inclusion of an antiferromagnetic J2 coupling. Now, on the ferromagnetic side, you see how complicated the situation is. You start, and if I try to do an extrapolation with just 2 Lanchar steps, I go way up in the sky. I no longer converge to even close to the ground state. And you see that the convergence is not very straightforward. It's highly non-monotonic under the application. So telling you that the Dirac state no longer represents a good variational description of the ground state, okay? And it's not smoothly connected. Indeed, as I said, the overlap between the Dirac state and the exact ground state is only 6%. It falls from 87% to 6% the moment you introduce a ferromagnetic J2. Now, so coming to the end of my talk, these are the conclusions. For antiferromagnetic values of the next nearest neighbor super exchange, the Dirac state remains stable up to around 10% of J1 coupling, introduction of a J2, which is around 10% of J1. Although a first order transition is found, a continuous transition between the state is not forbidden from field theory arguments. Also, the Dirac state faithfully represents the exact ground state on the antiferromagnetic side, okay? And this follows from a direct comparison of the exact calculations on small clusters. The ferromagnetic side, as I said, is more problematic. The Dirac loses accuracy completely, and it no longer represents a good state, at least on 36 sites. But we were unable to find any better state. So we tried various perturbations to Z2 spin liquids, to chiral spin liquids, to nematic spin liquids, to various dimer states. But unfortunately, we were unable to destabilize the Dirac state. So we could not find a better low energy description, variational description, there. But it's clear that the Dirac is not the answer. So there must be some other state, and it asks for future investigations. And finally, is that it basically means that the nearest neighbor Heisenberg point is at the crossroads between different quantum phases, including gapless and magnetic phases, but possibly also VBC, chiral, or even more exotic possibilities like lattice nematic states or others. And finally, the million-dollar question is to address in the future is to explain the origin of the various singlet states that populate the low energy spectrum, right? So the high density of singlets. This has not been explained so far. So I hope that our work has given some insights into not only the nearest neighbor model, but what happens to its fate under inclusion of one type of perturbation. So I'd be happy to take some questions now.
Thank you, Yasir. Ravi?
Yeah. Hi, Yasir.
Yeah, hello, Ravi. Hi.
So there is a question about the variational Monte Carlo approach that I had for some time, which I never got a satisfactory answer to. So you basically take a mean field ground state, and then you go Gutzwiller project, and then you do a Monte Carlo to bring it to the spin space, right?
Yes.
Now the question is, do you have any proof that the mean field ground state is the state which will give you the best variation energy after projection? I mean, how do you know that if you pick some other state at the mean field level, then after projection, it won't end up with a lower energy?
Oh yeah, so actually we go through the entire classification of mean field, fermionic mean field ansatz from the method of projective symmetry groups. So as I answered to Arnab, you basically fix the gauge group. You want a U1 spin liquid, you want a Z2 spin liquid, you want SU2, and then which symmetry do you want? Do you want a fully symmetric? Do you want nematics? Do you want chiral? There's an entire tables of classification which have been done over the last decade or so. So at least within the SU2 Abrikosov pseudo-fermion representation, we know what are the symmetry allowed mean field ansatz. So I know, for example, if you fix the U1 gauge group and everything is fully symmetric, there are only 4 states that are allowed. The uniform RVB state, which has a spin-on Fermi surface, the Dirac state, and there are 2 other U1 states.
No, yes. Once you have settled on an ansatz, you still have to pick that 50, right? That is probably the ground state of the underlying mean field Hamiltonian once you have picked your chi-ijs, for instance.
Yeah, so the chi-ijs are fixed, and then either if you include long range, there are variational parameters, right? If you've just fixed nearest neighbor, there is no variational parameter here. So I mean, so you optimize the state, right? You Gutzwiller project, and then you optimize all the variational parameters that are present. So do I understand you correctly?
Starting out with after you have fixed your ansatz, you're starting out with a Hamiltonian that is bilinear in fermions, right?
Right, yes.
And that 50 that you're picking, on which you want to project ultimately, is the lowest energy state of that bilinear in fermion Hamiltonian.
No, it's the lowest energy state after Gutzwiller projection. That's what I select. So I go through all of the mean field states and I do projection, and I see which one has the lowest projected energy.
So you do a projection on all the states, essentially.
Yes. All of them. I never look at mean field energies because, of course, they are let's say meaningless. So I do Gutzwiller projection on all of these states, and I choose my state which has the lowest projected energy.
Okay. So this 50 is not a single state. It's the whole. You essentially look at all the whole band and then basically choose the.
Yeah, I go to tens and hundreds of states. Let's say yes. So all that are there in this thing, and finally pick the one which actually gives you the lowest energy after projection.
After projection. Okay, fine.
Yeah.
Okay, Tanmay.
Hi. Yes. In the phases where you see these Dirac states are probably being gapped. So here the Dirac states, gapless Dirac states arises because of the sublattice symmetry from your lattice. I was wondering when this Dirac state become gapped, is it associated with the sublattice symmetry breaking? And because I mean, otherwise these are all nearest neighbor hopping, so one would get a quadratic term in the spatial derivative. So, but because of the sublattice symmetry, you get a linear derivative term, and that's how Dirac fermions arises in this sort of system. So that's one question, whether this is associated.
So let me answer this. Just to see if I understand. So the thing is that in order to gap out the Dirac cones, you must introduce some pairing terms here. Okay, so you must have delta ij C dagger, right?
Yeah, pairing or like coupling between the two chiral modes. The Dirac
you can have coupling, yes. So yes. I mean, right. So I mean, so that is So there are various ways. I mean, you can have introduce chiral terms, other things, whatever. But let's say the simplest is to introduce say singlet pairing. Okay, and if you introduce a singlet pairing with the correct symmetry, the correct sign structure, right? Not necessarily S wave, but it could be more intricate. And then there are various ways of going into Z2 gapped spin liquids as well as gapless spin liquids. Yeah, I mean, and then I mean you have to optimize your ratio of pairing over hopping. right?
No,
So
Z2, yeah, if you want to go back from U1 to Z2, then you have to also tamper with the gauge fixing that you did.
no. Which gauge fixing?
Probably the question is more of a technical type, so maybe you guys can discuss it offline.
Yeah, sure.
Yeah, I think that will be better. So Arnab, if you have a very quick question.
Yeah, sure. I'll ask a quick question.
Sure.
So Yasir, so when you were talking about this ferromagnetic perturbation, of course, you stressed that the Dirac variational wave function no longer seems to work well, even for small J2. But I didn't understand from your numerics how you could conclude the gaplessness of the phase. Maybe you can expand on that.
Okay. Sorry, maybe I didn't clearly specify. So one thing is from Lanshaw's 36 site ED. It's clear that on this cluster, the overlap of the Dirac with the exact ground state is almost negligible, right? Now the thing is that I still find that the best low and best ground state variationally that I can construct is the Dirac spin liquid. Although there must exist a better state, which is maybe obtained by perturbing the Dirac state in some way, either by chiral terms or Z2 or dimer, whatever.
No, I understand that part. Yeah, but I didn't understand that in your phase diagram, you sort of stressed that the phase is still gapless. How did you conclude that?
Sorry. Did I say that? No.
Or maybe I misunderstood.
Maybe it was my. So all I'm saying is that variationally, the best state I can construct is still the gapless Dirac, but it no longer represents this thing.
Okay.
So somebody has to do a better job, and there must exist something better.
Okay.
Yeah, which could be gapped. I mean.
Okay.
Yeah. Thanks for mentioning this.
Okay, so let's thank Yasir and actually all the speakers of this session for very nice talks. We have overshot a little bit of time, but I think it's worth it with the nice questions and answers.
Yeah. Thank you so much. I'm sorry for the delay.
No problems. Okay, thank you everyone. So over to organizers if they want to make any announcements.
Sure. Thank you, Sanjeev, for chairing the session. And we must apologize for the first 15 minutes of hotspots from our end because of some technical issues. So, and we thank all the speakers for very nice talks. So let's, I see that all the speakers for the next talk are there. So let me thank Sanjeev again and maybe, hello, yeah, okay, so maybe there's some echo. So what we can do is maybe in 5 minutes time we start. So I'll go ahead and make all the speakers of the next session as co-hosts. So Kalpataru, you're around, right? Okay.
Hi, Anamitra, can you hear me?
Yes, Shubhro, hi.
Hi, Anamitra. Can I just test the projection of my slides once and see if it's working?
Yeah, I'll go sequentially through all the speakers.
Okay.
Just hold on. That's someone is. Just give us a second.
You can mute from you.
So we'll go sequentially. Ajit, hi, this is Anamitra. Hi. So you can go ahead and check your slide, and yeah, I can see the thing.
Okay. Is it also moving?
Yeah. Yes, it's also transiting.
Okay, great.
Okay, thank you. So Udit. Hi, Udit, can you hear me? Hello.
He's muted, I think.
Yeah, I think maybe he's not. Let's move on. We'll come to him in a bit. So Utpal.
Yeah, hi. Can you hear me?
Yes, I'll just make you a host.
Just try. Yeah, can you?
Yeah, Utpal, go ahead. Yeah, I can see your video. Maybe you can share the screen and check it once.
Yeah. Do you see my screen now?
Yeah. Yes, I can see your screen. Maybe can you get it? Can you mute this one? Sorry about that. Yeah, I can see the transition as well.
So I'm sharing. Okay.
Yeah. Thank you. Shubhro.
Yeah. Hi.
Let me make you a co-host. Yeah, go ahead.
Somebody is coming from now, they will not be able to hear you.
No, this is okay. Hello. Tell on to switch it on. Shukru, I can see your slides and
Okay.
I
Can you see it now?
Yes. Yeah.
And is it transitioning?
Yes, correct. It is.
Okay. So then I'm fine, I think.
Sure. Thank you. Ajit, maybe you can keep your slides shared in.
Okay.
Hi.
And
Is it
Kalpataru, you are there. Yeah, it's visible.
It's in full screen mode?
Yes.
Okay.
Kalpataru.
Yeah.
Okay, so maybe in 1-2 minutes we can start.
Let's 11:25 will start. Okay.
Okay, so 3 minutes from now we'll start.
Yeah.
Sure. Okay. Hi Ajit, there is a little bit of echo. Can you just speak and just check the audio?
Okay.
Yeah, I mean, fine. We are hearing some echo, but you can hear us clearly.
I can hear you, yeah.
Yeah, okay, so I think that's fine. I think it's a temporary issue. So.
Okay. So I'll go back to sharing the screen.
Yes. Okay, so let's start this session. So good morning, everyone. So I'm Kalpataru from SINP. So in this last session of this meeting, we'll have 4 talks. The first one is from Ajit from IMSC. So please, Ajit, you can start your talk. So we have all total 25 minutes questions and talk.
Okay, and you will give me a warning around 18 minutes. Sir.
Okay.
Okay, good. Okay, so let me start out by thanking the organizers for inviting me to present our work. So I'm going to talk about fractional quantum Hall states that lie beyond the composite fermion paradigm. So this is work done in collaboration with Satitha Mukherjee and Kwan Park, who are at the Korea Institute for Advanced Study, Janendra Jain, who's at the Pennsylvania State University, Mark Rudner, whose postdoc I was when a couple of years ago at the Niels Bohr Institute in Copenhagen, but he's now moved on to the University of Washington in Seattle, and Messam Berkeshli, who's at the Joint Quantum Institute in Maryland. So I'd like to thank generous funding from the Woolen Foundation, Mark CRC grant, and a special mention to the diagram package, which we use extensively for our numerics. Okay, so here's the plan of the talk. So before we go beyond the composite fermion paradigm, I would like to say a few things about the composite fermion paradigm, since many of us may not be experts in this. And then I'll go to the main part of the talk, which is about the second Landau level FQG, which I will show can be captured by a different kind of framework, which is so-called the Parton framework. And I'll end with some conclusion then outline. Okay, so the fractional quantum Hall effect in the lowest Landau level. So when I say lowest Landau level, I specifically mean gallium arsenide. So throughout this talk, you should think of gallium arsenide, but results from this talk can easily be generalized to other materials like graphene and so on. So in the lowest Landau level of gallium arsenide or other conventional semiconductors, the fractional quantum Hall effect predominantly occurs at fractions of this form, n over 2p n plus minus 1. So here is the 1/3 state, which was the first observed state, which was fairly quickly explained by Laughlin using his eponymous wave function. Then there are states observed at filling fractions like 2/5, 3/7, 4/9. And also there are states seen at whole conjugates, so at filling factors like 2/3, 3/5, 4/7, and so on. So these whole conjugates have to be understood in the following way. So in any given Landau level, you have the symmetry called the particle-hole symmetry, where you can exchange the electron orbitals for hole orbitals. So any state at filling factor nu can be mapped onto another state at filling factor 1 minus 3. So for example, the particle-hole conjugate of the Laughlin state explains the 2/3 fractional quantum Hall effect. So how do we understand these fractions? So this was understood using Jan's proposal that the fractional quantum Hall effect of electrons is the integer quantum Hall effect of certain emergent fermions called composite fermions. So composite fermion by definition is a bound state of an electron and an even number of vortices. And vortices in many contexts behave like flux quanta. So you're also welcome to think of a composite fermion as a bound state of an electron and even number of flux quanta. And in this schematic, I chart the golden path to go from the integer quantum Hall effect to the fractional quantum Hall effect. So you start with some electrons at some small magnetic field. Then to each of these electrons, you bind 2 flux quanta to turn them into composite fermions. And then what you do is that you slowly smear out this flux quanta and merge it with the external magnetic field. So in this process, in this last step in going from B to C, you kind of hope and pray that the gap does not close. Because that's kind of what you want to do. You want to describe a system which is of interest, the right-hand side part, which is electrons in a strong magnetic field, the fractional quantum Hall regime, in terms of some weakly interacting particles. Okay, so now you can also run the tape backwards. So I start with a system of electrons at a very high magnetic field. Then from this external magnetic field, I grab 2 flux quanta and bind it to each of the electrons. So then I end up with a state of composite fermions in a small magnetic field. And to the 0th order approximation, I can just assume these composite fermions to be weakly interacting, actually non-interacting to the 0th order approximation. And then one can ask, what do these composite fermions do? So what we do is that just like fermions in some magnetic field in 2 dimensions, these composite fermions also form their own Landau-like levels. So these are called lambda levels. And whenever an integer number of these levels are filled, you get fractional quantum Hall effect of electrons. So this also allows you to relate quantities of the electrons with the quantities of composite fermions. So star quantities are composite fermion quantities. So the effective magnetic field seen by composite fermions is reduced compared to the magnetic field seen by the electrons. So B star is like B minus some flux quanta, the 2p flux quanta that you actually bound to turn electrons into composite fermions. And also the filling factor of the electrons is related to the filling factor of composite fermions by this relation. So now if you set nu star equal to n, which is n fill lambda levels, then you get fractional quantum Hall effect of electrons at n over 2p n plus minus 1. Okay, so till now everything I said was fairly qualitative, but you can also go ahead and do some quantitative stuff like calculate numbers, etc. And this comes about because of construction of wave functions, like microscopic wave functions. And the way to do so, the recipe to construct these wave functions kind of actually follows just from the integer quantum Hall mapping. So the idea is that you first start with an integer quantum Hall state, which I call phi n. This is just a standard slated determinant state, which we all know how to write down. Then you want to do this vortex attachment. So for that, what we do is that we multiply this phi n with this Laughlin-Jastrow factor, zi minus zj to the power 2p, so that every electron sees 2p zeros at every other electron. Okay, and then because we would like to work in this ideal limit of sending the cyclotron frequency to infinity, so everything is residing in the lowest Landau level, we kind of brute force project the state into the lowest Landau. So an amazing thing about this wave function is that even though this is like a variational wave function, it does not have any variational parameters. So once I fix the filling factor on the left-hand side, everything else on the right-hand side gets completely fixed. And another important feature of this wave function is that this can be evaluated to very large system sizes. And this is going to be very crucial for us. So a priori, if you look at a wave function like this, it seems like impossible to evaluate this for large system sizes, right? Because the way you kind of do projection in like Bhubaneswar projection or something like that is that you kind of expand the state into the full Hilbert space and just retain the part that resides in the relevant Hilbert space. But there's actually a way around it, and this is a little bit technical, so I'm not going to explain how to do that. But yeah, just keep in mind that this wave function can be evaluated for even like hundreds of electrons. Okay, so some of you maybe already noticed that at the simplest fraction, filling factor 1/2, there is no fractional quantum Hall effect. So in particular, if you look at these wave functions, they all occur at odd denominators because of this 2pn plus minus 1 factor. So why is it that there is no FQHE at filling factor 1/2? This can also be understood using the composite fermion theory. So in this process of forming composite fermions, you actually end up exhausting the entire magnetic field. So the effective field seen by composite fermions at filling factor 1/2 is actually 0. So just like electrons at 0 magnetic field, composite fermions also form a Fermi C-like state. So that's a gapless state, so you don't get any FQHE. But one should just step back a little and think about this carefully. So in the usual vanilla Fermi C that we are used to, kinetic energy is the main thing. Interactions are like kind of taken perturbatively. But here, this is like a Fermi C which arises completely from interactions. Actually, there's no kinetic energy to the problem, right? Everything is residing in the lowest Landau level. So there's no kinetic energy. But it is like kinetic energy of some emergent fermions, these composite fermions. Okay, so we also looked at these wave functions. So one might ask, how good are these wave functions? So how well do they represent the Coulomb problem? So for that, one can use many geometries and go ahead and do things like exact diagonalization and calculate variation energies or overlaps. So what I'm going to do is to look at one such geometry, which is the so-called spherical geometry. So a nice advantage of the spherical geometry is that there's no edge. So we don't have to worry about confinement and things of that sort. So there's just a compact geometry and it's all bulk, which is what we are interested in. And another nice feature about the spherical geometry is that there's no non-trivial genus to it. So all ground states are unique. So if, for example, if you look at fractional quantum Hall states on torus, etc., you get multiple ground states. So that those kind of things are not there on the sphere. So how do we construct the spherical geometry? So you go to outer space, get hold of a magnetic monopole and place it at the center of a sphere. And this generates a radial magnetic field, which is analogous to the perpendicular magnetic field in the planar geometry. So essentially what you do is that you take the plane and wrap it around on the surface of the sphere. So appropriate to this geometry, the orbital angular momentum and its z component are good quantum numbers. So this is what we use in diagonalizing in a given Hilbert space. Fix some LZ and then look at what states you end up. So a nice feature of the spherical geometry is that the flux particle relationship on the sphere is actually offset from the planar disk geometry. So for example, if you look at the planar disk geometry, the number of flux quanta is just directly related to the number of particles. But here it's offset. And this offset is the so-called Venn-Z shift, which actually describes how a quantum Hall state couples to curvature. So a nice thing about this shift is that many times you have like different candidate states all occurring at the same filling factor. And this shift can actually tell them apart because different candidate states may not couple to curvature, background curvature in the same way. So this is like a quantum number which can be used to label a state. Okay, so we also want to parameterize the interaction in some nice way. So this again was described by Haldane by introducing this concept of pseudopotentials. So what you do is that you place two electrons in some given Landau level, let's say lowest Landau level, and construct relative angular momentum state. So if you have like a spherically symmetric interaction, then relative angular momentum is again a good quantum number. And you look at what is the energy cost of placing two electrons in some relative angular momentum M state. And this energy cost is what we call the pseudopotential corresponding there. So throughout this talk, I'm going to look at single component fully polarized states. So the only relative angular momentum that matters is the odd relative angular momentum. So if you have like bosons or if you have like spinful systems, then you also need to take into account even angular momentum. So what the pseudopotentials look like for the lowest Landau level is shown here. So you have like strong repulsion at short distances, and then this decays in this typical 1/r. Okay, so with this, we can now go and check how good are the composite fermion states. So here are some overlaps of the CF states with brute force diagonalization of the lowest Landau level Coulomb problem. So the Hilbert space that we can access is about like 2 billion or so on. So one can go ahead and look at what is the overlap for, say, the Laughlin state. So this overlap is like almost unity. So like 0.9876. So for example, if I just pick a random vector in a Hilbert space of about 2 billion, then the overlap is going to be essentially 0. But here the overlap is like essentially unity, which kind of tells you that the state is fairly well captured by the variational ansatz. And this is true also for other CF states, for example, at 2/5, 3/7, and so on. And not just the ground state, one can actually go ahead and show that the CF theory accurately captures even like excitations and so on. So this is essentially what I had to say about the lowest Landau level stuff. So we should go a level up now. So onward to the second Landau level. Okay, so what are the fractions that one sees in the second Landau level first? So something dramatic happens in the second Landau level. So first important thing is that you start seeing some even denominator states. So for example, there's a very famous state at filling factor 5/2. So all the states in second Landau level are labeled as 2 plus some nu, because you have the lowest Landau level of up and down spins completely filled. So you can just ignore this 2 and then look at just the fractional part. So I have a state at filling factor 1/2, but that's not the only even denominator state. There is another even denominator state at filling factor 3/8. And also if you look at the odd denominator states, they also appear out of order. So you do see the state at 1/3, you do see some state at 2/5, but you don't see any state at 3/7, 4/9. So if you look at the Jan sequence n over 2n plus 1, then the way you get states is you go 1/3, 2/5, 3/7, 4/9, 5/11, 6/13, so on. But we don't get any of these 3/7, 4/9, 5/11, but 6/13 somehow shows up. So if you just look at the lowest Landau level sequence, then 6/13 appears completely out of order. Okay, so one can ask what actually is the difference between the lowest Landau level and second Landau level. It turns out that they differ in their Haldane pseudopotentials. So if you look at the second Landau level, the pseudopotential is slightly less repulsive at short distances. And this actually gives completely different physics. So for example, if you look at filling factor 1/2, one of the leading candidates to describe that state is the so-called Moore-Reid-Pfaffian state. And this can be thought of as a p-wave patch state of composite fermions. So we saw that in the lowest Landau level at filling factor 1/2, you get a Fermi C. So now if you make the composite fermions unstable to pairing, so this Fermi C then changes into a p-wave patch state. So it's p-wave because you only have fully polarized electrons, so they can't pair in the S-wave channel. So this is the simplest pairing. And again, if you go ahead and do this kind of calculation of looking at what is the overlap of the Moore-Reid state with the second Landau level Coulomb ground state, it's not like super high like you see in the lowest Landau level, but it's fairly good. It's like about 70% or so. Okay, so just like the Pfaffian, there is a close cousin of it, which is the so-called anti-Pfaffian. That is just obtained by just taking brute force particle hole conjugate of the Pfaffian. And it seems like if you break Landau level, if you break this particle hole symmetry using something called Landau level mixing. So for example, in any experiment, you always have some finite magnetic field. So there's always some possibility of the electron to hop into some higher Landau level or even lower Landau level. And that changes the interaction to some three-body interaction. So then particle hole symmetry is not a good symmetry anymore. And once you break particle hole symmetry, it seems like this is the state that wins over the so-called anti-Pfaffian. And actually, it's very difficult to construct this state because, again, just like projection, it seems like particle hole conjugation is super hard to construct. Right? You need the expansion of the state in the full Hilbert space, then change all the electron orbitals to hole orbitals. So it'll be nice to construct this anti-Pfaffian state in the Hilbert space in some neat way. Okay, so aside from phi-half, for every other state, it seems like there's like a new mechanism that one has to come up. So for example, it states at 7/3 and 8/3, which are like 1/3 and 2/3. It seems like it's either the Drest-Laughlin state or something called the Reed-Rezai state. So Reed-Rezai states generalize this idea of pairing of composite fermions into clustering. So you can have 3 clusters of composite fermions or 4 clusters of composite fermions and so on. So then at 2/5, there is some state called the Bondesson-Slingerland state, which seems to be relevant, or there's another Reed-Rezai state which could be relevant. Then that 3/8, it seems like there's some other state, some different version of the Bondesson-Slingerland state. And at 6/13, it seems like the best candidate is the so-called Levin-Halperin state. Well, the point of the slide is you don't need to know what these states are. The point of the slide is to show that in the second Landau level, it seems like for every state that you see, you have to come up with some different mechanism to explain it. So we set out to ask this question: can we find a unified description of fractal quantum Hall effect in the second Landau? And the answer turns out to be yes, in terms of what are called parton states. So what is the idea of the parton theory? So in the parton theory, you break the electron into fictitious subparticles called partons. And then because you're interested in gap state, you place each of these partons into an integer quantum Hall state. And then because you have to fuse these partons back to recover the physical electrons, you change all the parton coordinates to the electron coordinates. That implements this projection or fusion. So this results in wave functions of this form. You take a product of integer quantum Hall states, and again, I'm doing projection to the lowest Landau level because I want to look at states residing in the lowest Landau level. So even these second Landau level states can be actually written in the lowest Landau level with just some change in the effective interaction. Okay, so these parton states, given the filling factors of the partons, you know what is the filling factor of the electron. That's because each of these partons sees the same magnetic field as the external magnetic field, and they all have the same density as that of the electron. So that allows you to relate the filling factor of the parton to the filling factor of the electron. That also allows you to relate the charge of the parton to the charge of the electron. And this is like the simplest way to see that the Laughlin state carries E over 3 quasi-particles, because the Laughlin state is made up of 3 partons, each of them filling factor 1. And this filling factor is 1/3, but the parton filling factor is 1. So that's why you get minus E over 3 charge particles. So the composite fermion states are also parton states, where you get 3 partons, where one of them is at filling factor n, and then other 2 are at filling factor 1. Okay, so with this background in place, I can tell you what is the central result of our work. So we propose 2 parton sequences and their whole conjugates, which capture all of the second Landau level states. And a nice feature of these parton states is that they can be evaluated for very large system sizes. And this gives you new candidate states for 613 and 38, which haven't been looked at. So the way you write down the wave function for these parton states is you take some n bar, 2 bar, 1 cube. And this kind of notation actually translates into a microscopic wave function. So you take phi n star, by star I mean complex conjugate, times phi 2 star, and then multiplied by a 1/3 Laughlin factor. And these 2 states actually differ by a factor of 2 bar. So I'm going to discuss only the first ansatz here. And we look at the, if you are interested in looking at the second one, you can look at my paper. So let's just look at what is let's look at the first family of ansatz. So this is n bar, 2 bar, 1 cube. So this gives me states at filling factor 2n over phi n minus 2. So if you look at why we can evaluate these states for large system sizes, is because there's a way to project these states so that they become like factors of, they can be factorized into composite fermion states. And as I said earlier, you can evaluate composite fermion states for very large system sizes. So that's why you can evaluate these parton states also for fairly large system sizes. So for n equal to 1, you get the state at 2/3. So this is my candidate for 8/3. For n equal to 2, you actually get a state in the same universality class as the anti-Pfaffian. So this is like my way of constructing anti-Pfaffian for very large system sizes. And for n equal to 3, we actually get a state at 613. So this kind of shows why 613 is not, appears out of order, because it's not the n equal to 6 member of the n over 2n plus 1 sequence. It's actually just the n equal to 3 member of a different sequence. So let me show why the 2 bar square 1 cube is in the same universality.
18 minutes.
Yes, yeah, I'll finish in a couple of minutes. Is in the same universality class as the anti-Pfaffian. So firstly, as I said, you can calculate the shift of this state very easily. And this shift turns out to be in the same as the anti-Pfaffian. Then for small system sizes, you can also go ahead and calculate overlaps of these 2 states. And again, if you look at the overlaps of the anti-Pfaffian with this state, it's pretty high. Actually, it turns out for the phi half problem, this state is actually better than the anti-Pfaffian in terms of microscopics. So it's a better representation of the exact second Landau Coulomb Gaussian. Actually, here we can do something more. We can actually calculate what is called the entanglement spectrum. So Lee and Haldane conjectured that if you have 2 states that lie in the same universality class, the counting of the low-level excitations in the entanglement spectrum for them is identical. And we can again go ahead and do this for the anti-Pfaffian and this 2 bar square 1 cube state. And you see exactly the same counting, this 1135 counting, which is a typical characteristic of the edge excitations of these states. Okay, so here's a proof of principle of evaluation of these states for very large system sizes. So here I show the pair correlation function and the static structure factor for about hundreds of particles. I mean, this kind of calculation can also be done for the Pfaffian, because the square of the Pfaffian is a determinant. But I can go ahead and construct things like quasi-holes and quasi-particles, which you cannot do for the Pfaffian easily. Because if, for example, if you want to show that the state carries non-abelian anions, then you kind of have to create quasi-particles and quasi-holes and then take them around. And the wave function, which you can evaluate for very large system sizes, is quite useful for that, because that allows you to numerically illustrate braiding. Otherwise, in small system sizes, the issue is that these quasi-particles and quasi-holes can overlap, which kind of ruins the braiding calculation. Then for 613, again, we go ahead and look at this n equal to 3 member. And it turns out that if you can go ahead and compare this against the 613 Jan state, and these are topologically distinct because they carry different shifts. So that itself tells you that they're distinct. And we kind of get what we expect. So in the lowest Landau level, if you look at the energies of these 2 states, the 613 state actually has a lower energy. But in the second Landau level, this trend is reversed. So in the second Landau level, this 3 bar, 2 bar, 1 cube is what wins over. Okay, you can also place these 2 sequences in the form of a primary and secondary sequence. So both these sequence of states can be unified into a particular sequence. Just like in the Jan states, you have a primary Jan sequence and a secondary Jan sequence. You can put these 2 states together. Okay, so let me just end with saying, one might ask what makes these partons special. It's like, why these parton states and not something else? So this is a bit of luck and some experience. So what we know is that from the lowest Landau level physics, we know that putting more factors of 1 is good, because this factor of Zi minus Ej essentially keeps particles far away from each other. So that kind of builds good correlations in the many body states. And our states are like a simplest generalization of this. And instead of taking n11, you take nm11, and this m is like 2 or minus 2. But at the end of the day, this comes down to energetics. Just for the second Landau level, it turns out that these parton states are the most plausible. Given some random interaction, it's very hard to say which of the parton states will be stabilized. So that's an open problem. Okay, so let me end with the one-line take-home message. So almost all fractional quantum Hall states that we know of can be described in this very simple manner as products of integer quantum Hall states. So thank you for your attention. I'll be happy to take questions.
Okay, thank you, Ajit. So now we can have your questions. So Savinda.
Yeah, so the one question is regarding this, once you are in the second Landau level, you said the potential, the pseudo potential value goes down. Now, if we think of it, I mean, of course, if the first Landau level was some kind of a metal, then I can start thinking in terms of, screening or something which is helping me to kind of, get reduced Coulomb interaction in the second Landau level. But these are really insulators. So how should I think? And what is the physical picture one should think about?
Oh, that's actually not very difficult, because if you look at the single particle wave functions in the two lowest Landau levels, there's a big difference, right? The single particle wave function in the lowest Landau level has no node in it. These are just harmonic oscillator wave functions. And the second Landau level has a node in it. So if you have a node in the wave function, then what you can do is you can allow particles to come close together, right? Because the wave function can vanish them. Whereas in the lowest Landau level, you cannot allow particles to come.
I see, the natural way of vanishing it. So
yes, so you allow for some vanishing just because of the node. And that allows you to bring down the energy at close distances. Because, for example, these are essentially like integral mod psi square times the interaction. And mod psi square can vanish in the second Landau. It cannot vanish in the lowest Landau.
Okay, so I don't have to think in terms of screening and that kind of argument.
No, you don't. Actually, if you take the simplest form of screening, it doesn't do much.
Yes, that's what
it
I
either
think. So
reduces all the pseudo potentials, or if you just think in terms of like screening in terms of like changing the dielectric constant, then it doesn't do anything at all, right? Because it just changes the scale then.
Yeah. The other question is regarding the curvature effect you mentioned in the very beginning. Once you solve it on the sphere, there's a curvature effect. Now, just curious, how does it enter? I mean, think of free particles being solved on a sphere or on a cylinder. You won't know the difference because it will not couple to the background curvature. Now, how does the Landau level actually couples to the background curvature? For example, I can give another example. Let's say you take a spin momentum lock system. Then, of course, through the curvature of the momentum, the spin will know about it and vice versa, and then it will feel it. You see, the curvature has to kind of go into the quantum mechanics.
Yeah, so this is actually not something very easy to explain. So if you look at Chern-Simon series, then it's easy to see. Like if you look at Chern-Simon series of the quantum Hall state, then you see that there is a need for an additional term in the Chern-Simon series, which is the so-called spin
physical way of understanding it, as I said.
So the argument that people usually give, I don't follow that argument, but the argument that people give is that this curvature kind of serves like an additional magnetic field. But okay, I don't see why that is. But if you look at Chern-Simon series, you can see that you have to put this term, otherwise there are some inconsistencies.
Okay, thank you.
Okay, so I don't see any more raised hands. So let's thank you, Ajit, for this nice talk. So our next speaker is Udit Khanna. So Udit, please share your screen if you are here.
Udit, can you hear us? So what should we do? Should we move ahead, and if he comes around, maybe we'll wait for a couple of minutes.
Okay.
And have the other two talks, and then if he comes around.
Yeah, so we can move to Utpal.
I'll just write a message to him anyway. No, now his speaker is on. So maybe hello, Udit.
Can you hear me?
Yeah. So good. Yeah, you are a co-host, so go ahead and share your screen. So Kalpataru, take over.
Yeah, so Udit, so please share your screen. Let's see.
Yes, yes, I'm sorry for the audio issues. Just a second. Okay, do you see my screen?
Not yet.
Not yet. Okay. Okay. Let's see. What about now?
No.
Okay, I'm sorry. Just a minute. Why isn't it?
Yeah, now I can see a screen. So make it full screen and.
Okay, is it just a second? Must be a full screen. Is it full screen now?
Yeah, so now full screen. So let's start. So next speaker is Udit Khanna from Israel. So yeah, so please start. So you have 15 minutes all total. So I'll remind you at 10 minutes. Okay, so you have 12 minutes to speak and 3 minutes for questions.
Okay, thank you. And you can see my cursor, the mouse cursor?
I can see the cursor.
Okay, great. Okay, so let me start by thanking the organizers for allowing me to talk in this conference. I want to tell you about two of my recent works on the edge modes of quantum Hall states. So one of them on the integer quantum Hall states was published this year, and the other one on Laughlin states was the work was done in collaboration with Yuval Geffen from the Weizmann Institute and with Moshe Goldstein from Tel Aviv University. And I also want to acknowledge the group of Moti Heiblum, who's the students and the postdocs helped me understand their experiments in great detail. Okay, so this is the obligatory slide on the quantum Hall effect. We take it to the electron gas and
so Udit, I cannot hear you properly, and your slides are not moving, I guess.
Field. So as Ajit already explained, there will be quantum Hall
Hello,
phases at
Udit,
-1
can you hear us?
lambda level
Hello.
at a fractional fillings. You still see the title slide?
Okay,
Yes.
maybe
Hello,
he'll write
I
the
can hear you.
message.
Yeah.
Hello.
Just change your slides and check. Just do transition in your slides.
When slide 2.
I am changing my slides.
Can so now we can see. Yeah, okay. Fine now.
Okay, fine. Go ahead. Continue.
Okay, and you can hear me? Okay,
yeah,
good.
so we can hear you.
Okay, so okay, so we know that if you apply a magnetic field in 2 dimensions, the single particle spectrum is given by Landau levels, which have a gap. But at the edge, the Landau levels bend because of a confining potential, and they will cross the chemical potential at a certain point, which will lead to some chiral gapless modes, which are localized on the edge. And at least for integer Hall states, the number of states is expected to be filling factor. For fractional Hall states, if we describe them in terms of composite fermions, then we can use a similar prescription. Now, so it would appear that if you know the bulk filling factor, then simply fix the Hall conductance of the phase, and therefore it would seem natural to say that maybe the structure of the edge is also governed by the topology. However, what we learned in this project is that this is not completely correct, because the bulk topology only fixes some response functions like the conductance, but the structure of the edge could differ. Now, let me show you the main experiment which motivated this project. So it was published in 2019, and what they did is they so on the left I'm showing one of the geometries which they considered. So they took a quantum point contact, and on both sides of the quantum point contact you have a nu equals 1 phase, and you bias and these yellow squares are the ohmic contacts. So you bias the source, and so it means that there is some current which is flowing along this solid black line. At the QPC, there could be some partial tunneling depending on the voltage you apply to the QPC, and either the current could go on towards the contact G, or it could tunnel across, and we would expect it to go enter the drain D1. And transmission as a function of the gate of the voltage on the QPC. So you see that when the voltage is negative and large, the transmission is essentially 0. So the QPC is closed and all the current is going from S to G. On the other hand, when the voltage is large and positive, the QPC is open, and you have all the current goes from S to D1, and you see a transmission of 1. As you pinch off the QPC, as you reduce the voltage on the QPC, the transmission falls, but somewhere it falls. It forms a plateau when the transmission is exactly 1/3. And what this is telling you, this is first of all, the formation of this plateau is very strange, because if you have a plateau, it implies that there is a 1/3 mode which is being transmitted through the QPC, but at least the orthodox pictures of at least we do not expect such a mode to exist from orthodox pictures of the nu equals 1 phase. The inset in panel A shows so if you park if you set the QPC voltage to be, let's say, -1, and you change the input current, then the panel A shows the conductance, which is measured in D1 as a function of the input bias. You can see that it is very stable. It is 1/3, and it's very stable. What is very interesting is that in this particular, if you park yourself at this point, you do not see a currentless noise, which is what you would expect on a standard plateau. You actually see some short noise, which is on this plateau, which enters the drain D1, and the panel B shows you. So from the power spectrum of the noise, they can actually extract what is the Fano factor, which is expected to be the which perhaps the Fano factor is the charge of the quasi-particle which tunnels across the QPC. And so very surprisingly, what they find is that the Fano factor is actually E. So this is a very surprising result, because it first of all tells you that maybe there is a fractional mode at the edge of a nu equals 1. But more interestingly, the quasi-particle which tunnels across the QPC seems to remember that it came from a bulk of nu equals 1, because the Fano factor is 1. Within the same experiment, they also created a Mach-Zehnder interferometer, and what they found is that if the filling factor is 2, then you can see very nice interference pattern as a function of the voltage on this modulation gate, which essentially changes the length of the path inside the and however, as you reduce the filling factor, visibility of these oscillations, they go away. And what is important is that this visibility it never recovers. So they are not able to see Mach-Zehnder interferometer interference for any any quantum Hall phase in the lowest Landau level. Now they also so after our work on nu equals 1 was done, they also told us which they had done. Hello,
Udit, can you hear me? So your 10 minutes is over. So you have all total 5 minutes. Yeah.
Hello.
Another 5 minutes you have. 2 plus 3 minutes. So 3 minutes per question and 2 minutes you can finish your talk.
I see. Okay. So let me hurry up. So they also told us about an earlier experiment on the nu equals 1/3. Okay, so this is a very okay. So this was a complicated experiment, but the simplest thing which I will tell you is that if you bias the drain SC, then you inject some charge current here, the blue line, the solid blue line. But what they found is that there is some noise in the upstream. They found that there is some so all the current which crosses the QPC, it enters ACE, but they found a non-zero noise in the drain ANE, which is very strange because it tells you that maybe there is some noise going in the direction opposite to what you expect. Okay, so essentially, let me just say that I only presented one or two experiments, but there have been a series of experiments on the nu equals 1, which find some very strange results, including one recent one from the group of Biswajit Karmakar. And essentially, there are two things they find. One is that you could have fractional modes at the edge. And the other is that maybe there are some upstream neutral modes. This is at nu equals 1, and some of these are also present at nu equals 1/3. Okay, so the main question we ask ourselves is whether it's possible to have some kind of phase transition at the edge, which can give rise to this kind of a picture. And it has been known for Shemon and XG-Wen. And what they found is as the confining potential becomes smoother, you can develop a side step of a nu equals 1. So in the occupation, the electronic it has some non-monotonic behavior as a function of the guiding center. So we decided to study this problem again, and we are going to employ the disk geometry with a fixed number of electrons, and the confining potential is going to be generated by some parallel plate capacitor model. We will restrict ourselves to the lowest Landau level, and so the Hamiltonian is just this confining potential with the Coulomb interactions. Okay, so first thing we did is just exact diagonalization. The best we could do is 20 electrons. And what you see is that if the edge is very sharp, if then you see the standard nu equals 1 picture, because the average occupation is 1 in the bulk, and then it is 0 at the edge. But if the confining potential becomes smoother, then you see something crazy. What? Because even 20 particles are not enough to tell us. So what we did is a variational calculation. We took two forms of variational states, essentially product states.
So Udit, can you hear me? Yeah, so he's back. Maybe.
No, he's coming back.
No, he's coming back. Maybe he got locked out. I have to make him co-host again, I guess.
Yeah.
Yeah.
No.
Yeah, he's co-host already.
He's co-host already. Yeah.
Yeah. So Udit, so if you can hear me, please. Yeah, Udit.
Yes, I'm sorry, I got cut.
Yeah, so please share your screen, and you have to finish the talk in 2 minutes. Please, we are running late, so you have 2 minutes to finish the talk.
Okay, very good. Okay, so so essentially we did a variational calculation with these two ansatz, and I will skip the details of how we did the calculation and just go to the results. So if the edge is very sharp, then we obviously expect the standard picture to hold. And so we have a single droplet of nu equals 1. And what this means is that there will be a single chiral edge mode. However, if the edge is a smoother, we found that there is a reconstruction. There is always a side strip of nu equals 1/3. And if this is the ground state, it means that there will be 3 branches of low energy excitation. And one from the bulk counterpowering pair of
So Udit, we cannot see your screen now.
Hello.
Yeah, so we cannot see your screen now.
Yes.
Yeah, so we can see your screen. So your total time is over. So please, within 1 minute now, just 1 minute.
Yes.
You cannot finish all the
Okay,
37
okay, but-
slides definitely. So please 1 minute, in 1 minute.
Yes. Okay. So let me let me just say that the main result we have is that the edge of a nu equals 1 can reconstruct, and what we have found is that there is always a it always prefers to have a fractional phase at the edge, and so then if you believe this, then you can study the transport properties of this edge structure, and you can make some further analysis to show that actually the structure of the edge would be you'd have 3 modes: an outermost E/3, a 2E/3, and an upstream neutral. This neutral is some kind of a dipolar mode, and using this kind of an edge structure, you can actually explain the results of the high Bloom experiment, not just the fractional plateau, which is I guess very easy once you have the E/3 mode, but also the Fano factor of 1. And essentially the upshot is that the stochastic noise on the plateau is generated by the neutral modes, and the Fano factor is 1 because you end up, even though only one of the modes is being transmitted, because of the neutral modes, you end up with a noise on both the charge channels. And so the Fano factor always corresponds to the bulk filling factor if you have neutral modes. Then we repeated this similar exercise on nu equals 1/3, and we found a very similar result that essentially a fractional filling is always referred, which would imply that there could be neutral modes even at Laughlin states. It would have very similar experimental consequences. So okay, let me just summarize. And
So okay, you can put the slides there. So now,
okay.
Thank you, Udit. So maybe one very quick question if somebody has.
Okay.
Okay, thank you, Udit. So we'll move to the next talk. So next talk is from Utpal Bhai from IIT Patna. So Utpal, please share your screen. Can you hear me?
Yeah, I'm just sharing my screen. Am I audible?
Yeah.
Is it visible from your side?
Yeah, so please make it full screen now.
Yeah.
So I'll remind you at 18 minutes. Okay. So 18.
Yeah. Okay.
Yes, sure. Thank you.
Yeah, so thank you, Dr. Pradhan. And let me also thank the organizers for inviting me to present my works here. And it is always, very nice to be a part of these exciting meetings since last several times. Yeah, so today I'll be talking about quantum simulation with ultracold atoms and coupled disorder optical lattices. So this is the Department of Physics, IIT Patna, and I'm sitting here now. This is my cabin. So yeah. So because, I have observed that there is not too many talks on this system. So I thought that I'll kind of devote a couple of slides to mention that how we address the problem particularly. And then before going to some examples. So as we all know that, the theoretical discovery of BEC, Bose-Einstein condensate, happened in 1925 by our S.N. Bose and Albert Einstein. But then, it took very long time to realize the system in experiment, because there are a lot of hurdles in, choosing an appropriate system, and then also, cooling it below critical temperature, which is a very low temperature. In fact, this is the coldest temperature in the universe. So in 1995, this was the first, observation by Wolfgang Ketterle and Cornel Weyman separately, for sodium and rubidium atoms. They have observed BC, and then after that, a lot of other combinations of species have been experienced this condensate in different labs. So this was a Nobel Prize because of the remarkable achievement in 2001. So they have three of them shared the Nobel Prize in 2001. So few salient steps, I would like to point out here, but I also want to mention the sequence in which I want to put them up. So first thing is that we have to remember that the condensation is purely of quantum origin. So there's no classical counterpart, is because this is found of the fundamental properties of quantum mechanics, which is the superposition principle. This is the unique, which is not there in classical physics. So the atoms, the constituent atoms, they lose their identity, and as a whole, they have a giant atom and a single state, which is localized and stable, and which is called Bose-Einstein condensation. And then what is the specialty of this system is, it is not only a quantum system, a giant matter wave, it is also a highly tunable object. And it is also high, having high level of coherence. The reason is that this system is kind of feasible to outside lasers. And lasers are very much tunable, so one can actually tune the system and control the dynamics by actually tuning the outside lasers. And it has been observed that it is a very stable structure. It can sustain the structure even for several minutes. So the coherence is quite robust in this system. So these are the two properties for which one can, for any system, you always kind of look for these two properties for applying to technological applications. But then the third one is that we understand this obviously because the BEC occurs in very low temperature. So the momentum is almost zero. So it is a condensation of in momentum space, not in coordinate space. So in coordinate space, if you go ideally to absolute zero temperature, you cannot predict anything in the coordinate space. However, there are ways, like I'll point out these things, and how you can control the dynamics even in spatial coordinates. So this particular couple of works, it is actually starting from, it is not possible without mentioning the Richard Feynman in this case. And he mentions that maybe we can use another simpler and better controllable quantum system to simulate, understand, and control this phenomena. So the word better and controllable, so controllable comes from the tunability of the system, which is already there. And better means the stability and the robustness for it is having all the quantum nature, quantum properties, which may be useful for applications. Yeah, so to go ahead with this, how we address ultra-cold atoms. So that is the question we have to mention it here. And here actually I have picked up some examples. There are many more in recent times, 2-3 new directions where it is found, but I have not included those pictures here. But salient things that I'll just point out that soliton is one of them. and then you have vortices, Faraday waves, and so all the different directions, insulators, and superfluid transitions, atom lasers, Anderson localizations, negative absolute temperature, gravimeters, and applications in space and so on. So atomic beam splitters, and there are many, many applications of this kind. But why I'm mentioning all this is that if you apply external confinement to the system properly, and if you can tune them experimentally, then you can actually control the dynamics, and all these applications are somewhere related to, by tuning the external trap. So that was the point which I wanted to mention here. So just give me a second to change my pointer tip to some other color because it's not visible. Yeah. So now I think this is fine. So after looking at these applications, which depends on that tuning of the external trap, let me go ahead with how do we approach theoretically to this system, because this system is the experiment in this system is much ahead of the theory. And there are a lot of experiments already have gone through with different kind of direction, but theory is a bit less in number because this system is nonlinear and difficult to handle in presence of external confinement. But unless you have external confinement, if you recall the points, the number 3, where I said that this is completely in momentum space, not in coordinate space, but then to control in coordinate space, you have to have a feasible trap which can control the dynamics. So let us see that is a fundamental theory of BEC. Just one slide I want to mention because there may be students, postdocs, and who may not know, may not work in this field. So is a second quantized Hamiltonian, which takes care of the single particle Hamiltonian as well as the interaction term, which is given by BRR prime or URR prime. But when you think that this is a short range interaction, we actually arrive at this equation, which is called the Gross-Witkowski equation. And this equation almost look like a Schrodinger equation, except the term which is given in the blue circle, because this red circle term, which is already there in the Schrodinger equation, but the blue circle term makes the life completely different. This comes from the atom-atom interaction. So this is the one which gives you the nonlinearity, and the red circle which gives you the external confinement. And we will actually address here, we can tune the dynamics by changing this nonlinearity and also by changing the trap. But most of the applications, is carried out experimentally by tuning the trap. However, if you change the trap, there is also a passive change in the nonlinearity in the system. That is also well understood. Yeah, so there are some works of ours in recent time which will be somewhere mentioned in the in this presentation. So that's why I have given this reference here. Now this is to show you the robustness of external confinement. So here, if you look at the first plot, and you see that this is there is a gray circle over there, annular path, and this is the trap. This is the minimum of the potential, and you have a harmonic confinement, and over that you have a Gaussian peak in the middle, and this is a very routine thing observed in experiment, and this is also a replica of some experimental plot, but this is our plot where the BEC is kept somewhere here initially, and then you allow the BEC to evolve. Now what will happen if you allow them to evolve? And then it goes to, and if you observe, these are some time snapshots, that there are 10 splits. You have 10 BECs in the toroidal path, and then it happens at some particular 1/20th of some particular time. The time is called the revival time. So when all of them regains, and they combine to form the initial condensate again. And this phenomena is actually called fractional revival. It's a very well-studied phenomena in molecular systems and other systems, governed by nonlinear energy spectrum. But in ultra-cold atom, this is the first time that we address this. We report this, that we can also have a fractional revival. Not only we can have it in a much better way compared to other systems, because that you can see even 16 breaks up of the condensate, even more than that, and they are well distinguished from one another. So observing them for very higher order fraction revivals are also possible. And this is the figure B is kind of a Benzian state. You have 6 components of it equally situated on the circular path, and it happens in different snapshots. The times are also given in a millisecond. And if you look at the autocorrelation function, you actually get the whole picture. So these numbers, all these numbers are the number of splits you have. So when you go for so the half of the revival time, you get the condensate split it into 2 mini condensate, and they look similar but smaller in size because of the conservation of probability. So these are the numbers, and then you can actually identify that all these larger peaks are responsible for different fractional revival instances. However, there are some peaks where there is no, there is a time instance where there is no peak, but you have numbers. For example, there's 3, and there are several more. So these places are because they are falling. The phase is different, so you get a splits up of this number, but then you don't see any peak on the autocorrelation function. So this is also a very kind of different feature you observe in autocorrelation function for this kind of phenomena. But it is tuning. It is happening because you tune the trap in toroidal shape. Yeah, so this is the revival time which we address, and then fraction of it, P by Q, will give you any time where you can decide that how many parts it will be splitted in. Now, how to approach from the general solution of the system. So how to observe the dynamics in general. So if you look at if you compare this equation with the initial Gross-Pitowski equation, then what happens that you have the potential function, and then you have nonlinearity, and then we have also included some loss term, because you may have the situation that you are losing atom out of the system, and then to take care of that, you have another term which is given here. But we tried to put it all space and time dependent to keep the general approach over here, and then this kind of trial solution is well known, that you split it in the density part, and then you have some amplitude part, you have some phase term, and then this term appearing because of the loss. So there's nothing very special in this. It's a general expression. But then if you go for, I'm not including any of the derivations throughout my presentation, but some results only. And these are the consistency conditions you get. But then it is not so easy to solve these conditions, because all of them has to be found out properly, and those will be dependent on the external confining parameters. And we figure out this method. However, this is not that you apply any trap and then you figure it out. You may not be able to solve for some particular examples. We have given 3-4 examples here, but then for other examples, you may not be able to do it. So this is we call a unified approach, because one approach and then you combine a number of potentials in it. So this is another way of another trap control, where you actually address, we try to address a tunable double well trap. So because double well trap is very much useful for technological applications, and a lot of interference and logic gates and many things are implemented in this trap. So it is a tunable double well trap, I must say, but it is formed of very interesting terms in the equation that nobody has addressed the monomial terms, this j to the power j of up to 6 powers, combination of them, and then you have some trap which is controllable, which is kind of a Gaussian, and then altogether you give a very good tunability in the density profile. Yeah. So now let us get into the simulation with disordered lattices. How do we bring in the disordered lattices in ultra-cold atom? So the optical lattice, what is very familiar, that when we have the superposition of two lasers, and then from the standing wave, then you can actually trap neutral atoms, and then this is a very useful system for quantum simulation, and this is how we generate in experiments. So there are lasers, and then you can put it in. You can actually create some standing wave, and this is the potential for the standing wave. Now this is only for optical lattice. Now there have been a lot of progress for bichromatic optical lattice. So it means that you combine two different frequencies or two different wavelengths of optical lattices, and this is one of the examples that there are many examples of these lattices for ultra-cold atom. But then you have a short wavelength, you have a long wavelength lattice. So there are two optical lattices, but if you combine, you see that there are something interesting happening. You have some positions where you have disordered places, and this place is also sometimes called frustrated position, sometimes called disordered position. So they actually have quasi-periodicity when you combine two optical lattices, and then you can actually compare them to the system, condensed matter system, where you this kind of lattice structure appears like Hagom lattice, and then ratchet potentials and so on. So honeycomb lattice and so on. So there are different scenario experimentally done with the lasers. They can create with the lasers, which can simulate condensed matter system. And one beautiful example here, that in Nature Physics 2008, that they find very strong localizations over here for this kind of potential. So basically the localization happens here. So you have a spike in the density, and that is what is the experiment, but nobody addressed it in the theory. There are several atoms, but not much progress in that. So then we actually tried to address this part by looking at the general approach and taking the potential, which is a bichromatic potential. So one period is L, another is 2L. And then this is a common thing which happens in experiment, and V1, V2 actually is the intensity of the laser which can control from outside. Now I'll directly go to the solution we get, and then I'll tell that.
Dr. Rai, so we have 7 minutes all total, 2 plus 5.
Sorry?
18 minutes is over. So
yeah, okay, fine, yeah. So so basically we bring in the tunability of the system, that when you have the bichromatic lattice, you know how to control this V1, V2, and if it can be addressed in two ways. In experiment, one can play around with the intensity parameter and then see that how in what situation one can give a stable condensate in this kind of disordered lattice. And in other situation is, if you already have a relation between the intensities and the wavelength, you directly go for those parameters and you get a stable BSU over there. So that's the kind of target we had. And so we exactly address the tunability for those experiments which were done before this. And if you look at the profile, you have bright soliton here, but this soliton does not see the potential, because this is a very low, the depth is actually very low, so it is negligible. Then if you increase it, then the condensate, the atoms actually is able to, they are able to look at the potential. And then you see the position here, where actually they start coming to the disordered place, and after that you get a spike, and all the atoms will come to the center. So this is the place where you find a strong localization, and we confirm it by atom fraction and the energy term, where in atom fraction you can see that there is some term value of beta from where it is rising up and reaches to 1. So that means the total fraction of atoms is going to the disordered place. Yeah. So this is something which is in repulsive interaction. We actually propose for generation of bright solitary trains over here. Now, a new domain is that I'll quickly browse through this and very briefly that the domain of negative absolute temperature. So you always look for positive absolute temperature. We don't even mention that we are doing positive absolute temperature because that's the common scenario. But negative absolute temperature is very well known in statistical physics. When you look at the energy distributions formula, then what happens that if you increase the energy, the number of atoms or number of particles in the higher energy state, that will be reduced. But what happens if you get larger number of atoms in a higher energy state in equilibrium? So how do you explain that situation is only that you have to express T2 minus T, and then only you can express that situation. So you go from a positive scale to a negative scale of absolute temperature. But this was never achieved before because getting the higher bound of energy is very difficult in experiment. Theoretically, it was known, but experimentally, it is only in 2013 it was observed that, if you see this case, that if you increase the energy, number of atoms is increasing in the higher energy levels. So this is the Brun et al. Has done the experiment, but then Eldikar has beautifully explained them that, you have optical lattice like this, and then you have also the superimposed on some harmonic trap. Then you make them hot insulator and then invert them and then create negative temperature. So finally, this is the kind of potential what you have to create to find this kind of system. So now this is the harmonic trap and optical lattice. So now if you recall the essence of bichromatic lattice, that we found a very strong localization over there. And for getting negative temperature, you also need strong localization, stability. So why not converting these optical lattice to bichromatic? So this will give you a better model once we can do that. And so I'm not getting into this. The trap is a time dependent and is a complicated one, but then one can easily correlate to the coefficients and you can simplify because you need not to keep all this time dependent in the experiment. One can match with the experimental data, and we have done so. And then we have seen that there is a strong localization, it's a stable structure in the frustrated side, which is a better model for negative absolute temperature. And you can also have atom distillation here. You can actually hop from one side to another at a negative temperature. So this is the first instance where you can see atom distillation at negative absolute temperature. And we confirm this by entropy calculation and calculation of temperature. You can see the negative sign is coming over here. We can exactly say which parameter of the laser and the thing will change the temperature and how much. So this is the thing. And this is one more thing that in disordered lattice, if you look at the rogue wave, which is a very surprising wave, and knowing the formation mechanism and the dynamics is not so easy. Many things are not clear. But if you look at it in presence of them, and here actually I have mentioned only the vector BEC. So you have two components over here, and then you can actually find out the stable structure for both the components. So this is the first component, and this is the bright soliton and dark soliton. And this is the second component. If you see that localization also appears in time scale, so the whole dynamics is completely different from a normal condensate obtained in solitonic configuration. So definitely this disordered lattice for rogue wave will give you a lot of new physics, and which is probably not known so far. And if you look at the localizations, and that still appears, the Anderson kind of localization still appears for higher values of the trap parameters. So it is actually zoomed up because it is not visible here. So now this is the last one. I'll be finishing in 1 or 2 minutes now. So now the question is that what happens if I have two optical lattices or two bichromatic, two disordered lattice, and then couple them? So basically it is an entangled kind of scenario, but in terms of the optical potentials. So you don't have uncorrelated two or disordered lattice, but you have correlated lattices. And what happens due to the correlation? So this is again communicated. So I'll just mention briefly that how we address this. So let us go to the potential, and you see that these two parameters, beta 1 and beta 2, which we have named as B1, B2, can go from -4 to 4. But then you have here at 0 of one of the parameters, you get exactly a disordered lattice. Okay, but when you have a larger beta, positive or negative, you change it and you get disordered double well superlattice. So for positive value of B1 and B2, you get disordered double well superlattice. So you have a disorderness here, you have disorderness here. So this is a kind of a completely a new kind of lattice which can be generated if you couple two disordered lattice in this way. So just some snapshots, 2D snapshots, where you can have, as I said, that is a disordered double well potential. So you can have a bifurcation and periodic bifurcation of the condensate, and which you cannot see in other potential because you have a disorderness in between, which actually helps it to separate one condensate from another. So that helps in distinguishing the condensates in experiment. So if you keep it a normal optical lattice and normal disordered lattice, this may not be possible. So this is some snapshots where you can see a lot of interesting states over here. And you can see that superlattice, double well superlattice things are coming here. And then you can also have a tri-structure, then a lot of other kind of things which you can see here. So this is just for giving you some example that how the coupled lattice will act on the system and give you some interesting structure for quantum technology for that. I'm sorry. Take some water. Yeah, so this is the end of the slide, and so what we have done is that we have actually addressed the dynamics of the condensate in presence of disordered potential, and the disordered potential, the phenomena, there are plenty of phenomena which are actually people are concerned with, and we have addressed some of them where we have shown the single disordered lattice, then and the soliton and rogue wave in that, negative absolute temperature, and the coupled lattice. So this is my group, and this is mainly the work by Borun and Nilanjan. So where is my cursor? Yeah, Borun and Nilanjan, and these are MSc students, project students, and also the collaborator Professor Salasnis and Professor Panigrai and Dr. Ghosh. So these three people are also involved in these works what I have presented here. So I thank you for your attention. I'll be happy to take questions.
Okay. Yeah. Okay, thank you, Dr. Rai. Yeah. So we may have one or two couple of comments to quick questions. So sure. Please, if somebody has one.
I think there's a question in the chat box.
There's a question.
Oh, I see. So let me see that. Yeah, okay. So how the negative temperature we're talking about is consistent with the law of thermodynamics. Okay. So actually, you see, laser also have a similar kind of atomic inversion. All of we know about it. And then here, the difference is we create an equilibrium state in higher energy. So for that, your potential particularly will have to have the bounds, upper bound. So there should be some maxima in the potential, and you have to have a stable state over there. Then all the theories in thermodynamics that will follow. So there is no problem. But there you have to actually correlate with the temperature and the thermodynamic parameters. So going from this side, so definitely, in negative temperature, you have calculated entropy and temperature. So, and then you can also go ahead. We have not carried on that kind of calculation, but one can easily do that. So that is fine. Because the statistical physics, this negative temperature was known and all other things were known, but only thing is that was not observed. So people did not talk about the technological application in this domain. So that is the new thing what we are addressing.
Okay, thank you, Dr. Roy, for this nice talk. So now we'll move to next talk. So next talk will be by Dr. Subhasen Gupta from SNU. So Subhada, can you share your screen?
Yeah, just a moment. Is it visible?
Yes, you're sharing your screen. Okay. Yeah, so it's visible.
Okay, so I'll keep the video off just because there may be problem with bandwidth.
Yeah, sure.
So
Subhada, so we have all total 25 minutes, so 18 plus 18. I will give you a reminder at 18 minutes. Okay.
Sure, thank you.
Yeah, so please.
I
Subhada.
start by thanking the organizers for inviting me to this very interesting session. And they've been doing it successfully for many years now, even amidst Corona and so on. So I am Bhubaneswar Gupta from Shiv Nadar University, and the title of my talk is Universal Behavior of Multi-Point Spectral Correlations Across Spectral Crossovers in Stochastic Quantum Spin Chains. So let me start by first, acknowledging my co-workers. So most of the interesting work and hard work in this talk was done by my PhD student, Debojyoti, who is shown here. He's a very bright final year student. And my collaborator in this, because I'm new to this field, is Dr. Santosh Kumar, who is an expert in RMT. So this work that I'm going to talk about here has been now submitted to Physical Review B and almost accepted. So with minor comments. And there's another poster that was presented by Debojyoti on long-range spectral correlations, which was a follow-up of this work, and that is going to be submitted soon. And I thank the DST Early Career Project Award for funding. Okay, so because I'm new to the field and also for non-experts, let me start by giving a brief introduction to what random matrix theory is all about. So basically, just as you have probability theory for scalar random valued scalars, if you think of random valued matrices, then the statistics of their, an ensemble of them, then you can study the statistics of their eigenvalues and eigenfunctions. And that is the subject matter of random matrix theory. So apparently it has nothing to do with physics. It's a branch of maths. But a connection to physics was established, and it was probably first invoked in this context of explaining slow neutron energy levels seen in slow neutron resonance scattering from complex nuclei. The thing is, nuclear interactions are largely unknown, and the density is very large, and levels are very complex. So only generic statistical inferences can be drawn from there. Okay, so next I'll highlight the various regimes that will keep on occurring in my talk. The integrable regime, which is the Poissonian, and the three Wigner-Dyson regimes. Actually, two out of them will be referred to in this talk. So when we talk about integrable systems, which are also sort of exactly solvable systems, there is no essential demand on symmetry in this class. The levels are uncorrelated. There is no level repulsion, which is denoted by the index beta is equal to 0. And the levels are distributed independently. And the distribution of the level spacings is Poissonian. Okay, so it's basically the difference between two energy levels. Now I come to the three Wigner-Dyson classes. So the first one being the Gaussian orthogonal ensemble. So if you consider a Hamiltonian, which is invariant under a time reversal symmetry, and with t square going to +1, so that there is no Kramer's degeneracy. This is one of the situations in which such an ensemble will hold. The other one could be time reversal symmetry invariant Hamiltonian, but with Kramer's degeneracy when t squared is -1, in the presence of at least two more spatial symmetries. So these spatial symmetries actually commute with the time reversal operator and square to -1. So these are basically rotations about the x and the y axis, as you can see here, for example, and the mutually anti-commute. So under these circumstances, it can be shown that the class of Hamiltonians that satisfy one of these properties is real symmetric in nature. And the invariance class under which their eigenvalues and so on remain, unaltered is the real orthogonal transformation, ON or SON. And the levels are correlated with the level repulsion degree of beta equal to 1. So when I say beta equal to 1, you can think of it as, because it's a real symmetric matrix, if you consider a 2 by 2, then there's one parameter in the off diagonal that I can tune to, get the level spacing tuned. Okay, so in that sense, beta is equal to 1. Okay, the next class is the GUE, the Gaussian unitary ensemble. So this can occur in two different situations. When there is no time reversal symmetry at all, okay, and there is no demand on spatial symmetry in this case. The second is there can be a time reversal symmetry with t square equal to -1, meaning there is Kramer's degeneracy, in the presence of one and only one parity symmetry. So for example, rotation about the x-axis by pi. So in such a case, it can be shown that the class of matrices is complex Hermitian, and the invariance class is unitary, un, and the levels are again correlated, and the level repulsion degree is 2, because now the off-diagonal element has two independent components, two reals, right? Because it's a complex Hermitian matrix. There's also a third variety, which I'll not go into, where you have only time reversal symmetry as the symmetry, no spatial symmetries. So that is the class where the matrices are, quaternion real, and the class of symmetry transformations is symplectic. But since we'll not be using it here, I don't want to unnecessarily go into it. Okay, so now if you take an ensemble of these kind of matrices and diagonalize each of these matrices and then calculate the spacings between the levels, okay, and you can calculate these spacings, and then you normalize the spacings with the average level spacing, because if you want to compare different system sizes and different systems in general, you need to normalize this so that the average level spacing is 1. So this process is called unfolding in random matrix theory. And then it was the genius of Wigner who pointed out that these are the kind of, from general arguments, these are the kind of expressions that you would get for this normalized energy level spacing. So the uncorrelated one, beta equal to 1, is the Poissonian, which is shown by the blue plot here. And it has no level repulsion, because if you see, the highest probable level is where the level spacing is 0. Whereas in these two cases, GOE and GUE, this looks like some kind of a Gaussian-like factor weighted by power of s in the beginning, so which is the leading term in the expansion. So this is s equal to, s to the power 1, which is beta equal to 1, and this has more level repulsion, s squared. Okay, and you can see progressively, because the mode of this distribution keeps shifting to higher level spacings. So that tells you the levels repel each other. And the interesting thing is, irrespective of how from what kind of a distribution you draw these elements of the matrices, whether it's a Gaussian, whether it's some other continuous distribution, these things always hold. So there is some kind of a law of large numbers at play. Okay, now let's come to the spin system that we study, and we want to study these spectral crossovers in these spin systems by breaking the symmetry partially. So the first term is the usual Heisenberg term, nearest neighbor Heisenberg model. And the second term is a random inhomogeneous magnetic field, okay, in the z direction. And these HJs at every site are drawn from a Gaussian distribution with mean 0 and a variance of H, okay. And the third one here is a scalar spin chirality term, which is a 3-spin term, which can often arise in systems which have non-coplanar spins, okay. So this involves 3, spins at 3 different sites. And Deeptiman has a very classic paper from old times on this kind of a interaction term. So let me just point out that this third term can be simplified in this form, where because of the presence of I, it will render the matrix, otherwise real matrix, complex. And note that all of these terms will conserve the total SZ, because there is a S plus S minus term here. Okay? Let me also introduce quickly 2 different time reversal symmetry operators. One is the usual time reversal symmetry operator here, which is the product of the complex conjugation and this rotation by pi about Sy, which reverses all components of spin. And then you have another unconventional time reversal symmetry operator, which is basically this conventional one here, multiplied by a rotation by pi about the x-axis, okay? And this reverses only Sx. But this is still a time, this is good enough for a time anti-unitary operator in the sense of our previous classifications, because all we need is its commutation with H and its squaring to plus or minus 1. Okay, so now how do we reach the Poissonian regime? We'll keep only the Heisenberg term. In this case, this is completely rotationally invariant, but also it commutes with its time reversal symmetry invariant, right? Both in the conventional and the unconventional sense. So in this sense, if you remember the past classification, this should lead to the, I shouldn't say will, that we will see, it should lead to a Poissonian distribution, then there is no randomness here, okay? Now, the way we reach the Gaussian orthogonal ensemble, is the last line with last bullet point visible? Because on my screen, there is this thing with the pointer.
Not visible, last bullet.
It says no something. Okay. Okay, so yeah, So basically, we will reach the Gaussian orthogonal ensemble by taking the first two terms. Now, as you know, this HR, which is the random field, is not invariant under a normal time reversal symmetry operator, but it is invariant under the unconventional time reversal symmetry operator, because that only inverts SX, right? Inverts X direction spin. Now, so which means that HGOE defined in this form basically is time reversal invariant in the unconventional sense and squaring to +1, which we can achieve by keeping an even number of sites in the lattice, okay? So this is invariant under SZ is Hamiltonian, but it's not necessary, as we have seen, because if it obeys time reversal symmetry, you don't need any other, spatial symmetries. And there is no Kramer's degeneracy because n is even. Now, the third one we achieve by keeping all three terms, and this is neither invariant under the normal time reversal invariance nor under the unconventional time reversal invariance, and rotational symmetries are irrelevant, okay? Sorry. Oh. Yeah. So rotational symmetries are irrelevant. And this can also be, in passing, we note that this can also be achieved using the HGOE, which is basically this first two terms only. And then you have to go to an odd lattice, the odd number of lattice sites, but we don't want to do that. We want to compare the results. So we'll always, stick to this sort of a picture where we keep an even number of sites. Okay, in order to achieve the Poissonian to GOE crossover, we keep JT, the amplitude of the scalar chirality term, always fixed at 0. And then tune H, the magnetic field, the amplitude of the magnetic field, from 0 to finite to bring about the crossover, and everything is expressed in units of J. So now what we do is we basically take, one particular value of H, which is the width of the distribution from which this magnetic field is drawn. And from there, we draw n site magnetic fields. That is one configuration. For that configuration, we calculate the energy levels and then the spacings. And we then sample over many other ensembles, many other members of the ensemble by changing the configuration, keeping H fixed. Okay. And then all of these level spacings are plotted as a frequency distribution to get my the probability distribution of level spacings. And then one changes the width of the distribution H from which it is drawn, and then so on, one continues. So if you look at the results, I've shown some results here. So this is the case where H is 0. And this is, of course, the Heisenberg model, which is integrable. And you can see this is the result from the spin chain, this frequency distribution. And this black one is the Poissonian, which matches very well. And the third one is the GOE. Okay. Now, by H equal to 0.2, we reach the non-integrable or quantum chaotic regime. So this is basically for n equal to 14. And the number of basis states is 3432, since we restrict ourselves to SZ equal to 0 sector. That's the largest SZ sector that has representations from all possible S values. And one averages over 50 different matrices. So here you can see, by this time, the energy level spacing distribution exactly traces the GOE. Okay. But surprisingly, as we go to much larger magnetic fields, it again behaves like an integrable system and becomes Poissonian again. This is probably because in this very large limit, the quantum fluctuations are all suppressed when you get a more, Ising-like limit. So in a rising model in a random field, and then this goes back to Poissonian. So this can also be traced back to the localization of eigenstates in this many-body basis. Okay. Now, although these, I'd just like to point out in passing that although these level spacing distributions match exceptionally well with the GOE, if you now go ahead and plot the, so level spacing is basically a 2-point energy correlation. If you point the 1-point thing, the DOS, then you see for all these three cases, they look more or less Gaussian-like. Whereas the prediction from Wigner's, by Wigner is it should be a semicircle. The reason being that in random matrix theory, all possible off-diagonal elements in the matrix have finite values. But in your physical models, they have a very finite range. So it will never mimic the DOS in that way. Okay, so it's very important for our work to pin the exact point where the crossover takes place. Okay, so where exactly this goes into GOE. So to do that, we use the statistical measure called the Kullback-Leibler divergence measure, so DKL, which is basically given by this expression. So where P and Q are the two probability distributions, we want to see how well they tally. So this is a measure of how closely they match. when DKL is 0, of course, so when these two basically match, when they're exactly the same, this will give log 1, which will give DKL is 0. And if you take the analytical expressions for the Poissonian versus the GOE that I showed earlier, DKL comes out to be 0.28. So now if you look here, the results, it is n equal to 14. So at h equal to 0, basically, it should be Poissonian versus GOE, more or less. Of course, it's a physical system. It's not exact. So this number here is close to 0.23 or something like that. And with n equal to 16, that even crosses 0.25 going towards this value. And then this divergence falls off and then it goes to 0. So by the time it goes to exactly to 0, that is the crossover point, because then we have achieved. So this GOE for GOE would be 0, right? So that we have achieved it. And we also see that as you increase the lattice size, your critical field at which the crossover takes place decreases. Okay, now we want to map this onto, so we have seen that Wigner surmise tells us that at the endpoints, when you have perfect Poissonian, perfect GOE, there is well-defined, Wigner surmise analytical results, to which it maps, right? We have seen that here, for example. Now, in the intermediate regime, however, when we are, the crossover is not immediate, it's not discontinuous. So in the intermediate range, basically, we need to do a RMT analysis to see what kind of a function will map the physical crossovers onto RMT. So to do that, we resort to this Pandey-Mehta Hamiltonian. So they had shown long back that if you take a Hamiltonian of this kind, where you have a partial symmetry breaking parameter lambda, and the endpoints H0 are, for example, Poissonian, H infinity is the GOE. So Hamiltonian, in that case, if you take lambda tends to 0, this will lead to H0, and lambda tends to infinity or large will give you H infinity. So you can continuously tune lambda to achieve this crossover within RMT. And from an analytical treatment of these 2x2 Gaussian matrices, they had derived this exact expression for the crossover distribution of spacings, okay? So here, when lambda is equal to 0, you will recover the Poissonian expression. And when lambda is large or infinity tends to infinity, you will recover the GOE Wigner surmise. Okay, so this is some complicated function involving modified Bessel functions and so on. Okay, so now we show so earlier we had shown the extreme points of the crossover. So now we go over the crossover slowly. So here, if you look, the results shown in the red dots are the spin chain results, okay, this. And then the black and the green ones are the Poissonian and GOE, and this is the interpolating function. So these are the two extremes from RMT, and this is the interpolating function from RMT. So you can see the Poissonian matches extremely well here. Of course, we have seen that before. And so does it, match very well when you go into the GOE regime here. Intermediate, the match is quite good actually. So this blue one here is this function taken from the Pandey-Mehta Hamiltonian, and the red ones are your physical system results, and they match pretty well. And you see that match only improves if you go to a larger system size. So we should also note that as your system size increases, your SZ equal to 0 basis size increases, and you need lesser number of ensemble members to get a good statistics. And this is related to the principle of spectral ergodicity, which tells you that for large matrices, the spectral average and the ensemble average, spectral average for a single matrix and the ensemble average should merge. Okay. So anyway, so we see that over the crossover, this random matrix theory results sort of, matches very well with the physical results. Okay, so secondly, when we want to go to GOE to GUE, we keep H equal to 0.2, fixed at 0.2 to be well within the GOE regime already, and then vary JT from 0 to finite. And here again, you have this interpolating function again from a similar treatment from these references given below, and you have a function that interpolates between the GOA and GUE Wigner surmises, okay, as a function of lambda. Again, lambda tends to 0 will give you the real symmetric matrices, and this will give you complex Hermitian matrices. And of course, this addition of these two things, again, will have real eigenvalues because again, they're symmetric. So nothing changes that way. So we again see that there is a very good agreement all over the crossover, even better now, compared to what we had in the Poissonian to GOE. So this green one, so this is again, the red ones are the spin chain results. These two GOE and GUE are given by the black and the green lines, and this blue is the interpolating one. So first you start here with it's already in the GOE, and here it has already crossed over to the GUE, and here, this is the GOE sorry, this is the GOE, this is the GUE, and you find in between, excuse me, that in between, it matches this very well, the interpolating function, traces the physical system very well, and same is the case for n equal to 16. Okay, so again, here we have done the pinning of this crossover point using the scale divergence. The one thing that is a little different here is you should note that while Poissonian to GOE, the breaking of symmetry is immediate, so it starts just like that. Here, there is some kind of a stiffness in the GOE regime, so there is a threshold value of the physical parameter that you need to break the GOE symmetry. So this is shown by the plateau here, and then by the time you reach around here, you have crossed over. Okay, so again, I'm showing you results
Subodha,
here.
so we have already crossed 18 minutes. So this
Okay.
is the second.
Okay, I'll need a few more minutes. So again, here I show you the results, not only from 14 and 16, but also 18, for which has a overall basis size of about 50,000 if you take the raw basis. So we used global spin rotational symmetry to reduce that basis to half. And then you see again, the result that, I mean, these things match very well with the physical predictions, and the physical crossover parameter progressively decreases systematically as your system size increases. Similarly here for the JT term, okay? Now, yeah. So now what we can do is we can plot the physical crossover parameter, H here and JT here, for the Poissonian to GOE and GOE to GUE on the x-axis, and the RMT crossover parameter on the y-axis. Of course, beyond a certain critical value of H, it has already crossed over, so these values actually go and saturate here. So similarly for this one. But we have plotted it for all three lattice sizes. Now we want to do a finite size scaling analysis of this. So we see that if we multiply the physical parameter by the basis size raised to some exponent power, so some scaling exponent, then these three plots can be collapsed onto one universal plot here, okay? At least in the linear regime. And that gives you predictability of where the crossover will take place once you know the basis size. Okay, so this shows a beautiful scaling behavior that way. So it's universal in that sense. Okay, so I can't go into much details of this. We have also done, studied similar crossovers in 3-point spectral correlation, which is a ratio distribution initially proposed by Hughes and co-workers. So which is basically the ratio of two consecutive level spacings. And there, you don't require unfolding because it's already the ratio, so everything cancels out. And you have these Wigner-Surmise-like results from the, from the references shown here, which exactly are have a one-to-one correspondence to the Wigner-Surmise results in the case of the level spacing distribution. And Santosh Kumar and co-workers actually derived this result for the interpolating function for the GOE to GUE sometime back here. Okay, so we have an interpolating function like before. For the Poissonian to GOE, there is no analytical result available to our knowledge. So we use 3x3 matrix model. So we need at least 3 dimensions with 3-dimensional matrices because we need 3 energies, right, to have ratios. So that is denoted by EPO, this numerical interpolating function. So again, we find that when we do this analysis, this crossover is extremely well traced by the RMT results. Okay, so I won't go into the details of that. And it crosses over at similar numbers that you had for the spacing distributions. Again, you can do a scaling analysis like before for the 3 lattice sizes that I was talking about. And you again find that there is very nice scaling for the 3 lattice sizes, which makes it universal. And the scaling, moreover, the scaling exponents are very similar to the values that you had for NNSD. So in all cases, they hover around 0.25. Of course, we don't understand that fully exactly why. And this shows the robustness of the procedure. So without further ado, I'll just go to the conclusions. So we have studied crossovers between integrable and quantum theoretic limits of 1D spin chains. So basically between Poissonian to the Wigner dice and ensembles via partial breaking of symmetries in the physical model, and then trace them via the RMT, crossovers. And this match exceptionally well, which shows the generality of the RMT framework. But more importantly, we find that there is a very nice, scaling of the physical parameter with respect to the basis size that renders the plot of lambda versus the physical parameters system size independent. And not only that, irrespective of the type of crossovers, we studied 2 types, right? Poissonian to GOE and GOE to GUE, or the spectral measure that we used, nearest neighbor or ratio distribution. the scaling exponent seems to be almost the same in all cases. And right now we are in the process of looking at, integrable to chaotic transitions in the system by an analysis of the wave function, localization versus, delocalization in these wave functions. So I end by thanking you. That would be all, I think.
Yeah, thank you, Subhada. So now the session is open for questions. See if you have some raised hand.
Hey, Kalpataru, can I ask one
Yeah,
question?
so yeah, please. Yeah.
Subhada, this is Ashish. So in your Hamiltonian, this chiral term, that SI dot SJ plus SK. So is it means that the J is coming from, suppose if I translate with the Hubbard model, that is it coming from the next order thing, or?
Yeah, basically, I think if you do a canonical perturbation theory of the Hubbard model with a magnetic field around, then I think in the third order you get this kind of a term.
Okay, but this chiral order, this chiral interaction, it's a bit different, looks a bit different from the three-spin interaction term. So
what is the
maybe
three
somehow
spin? What is the three-spin
because of the third order term, it will come. The third order of this Hubbard model.
Yeah, but what does it look like?
So it will be SI-SJ and into SJ-SK, like that. And then there will be three terms. It's not like that dot in the cross.
Biquadratic.
No, biquadratic is different. Biquadratic is fourth order. Okay.
So multiplication of two dot products of spins.
Then two dot product will give scalar, and then you can multiply those three. Okay. So if you go from suppose 1 to 3, then you go 1 to 2, 2 to 3, and they can come back 3 to 2, 2 to 1.
Okay. So you have a 1.2 times 2.3, you mean?
Yes.
No, that's a fourth order.
No, fourth order is different.
So there are there are three spins still.
What is the scalar, Ashish? How are you making the scalar?
Scalar is on dot S2. That's
so basically this part
S2 dot S3.
This part is the chirality, spin chirality, and then you dot it with this, it becomes the scalar spin chirality.
No, but this breaks your chiral symmetry, but this spin will not break that thing.
S2 dot S3.
Okay, so this break that this can take plus minus one sign. Okay, that's why you can have the sometimes the positive and negative energy, and that breaks the symmetry.
No, actually, I think it will become a fourth order.
Okay, yeah. So another thing is that since it's a 1D chain, so you are saying basically that three spin which are basically 1, 2, 3 in the same chain, like
yes.
Okay.
So in more than one dimension, I mean, we were doing some calculations in 2D. So then you have these triangular plackets also that will contribute if you take a square lattice.
Yeah. Okay. Yeah.
Okay, so if I don't see any more raised hand, and is there any question in the chat box? No. So thank you, Subhada. So thank you for this nice talk. So now the session is over. So I want to thank you all the speakers. Now I hand over the system to the organizers. Anamitra, so please.
Hi. Thank you, Kalpataru, for chairing the session, and all the speakers for very interesting talks. So with this, we have come to the sort of end of this year's edition of the meeting. So we'd like to thank everyone for participating and giving their time, chairing sessions. So your participation, of course, is the thing that makes the conference a success. So thank you everyone once again. Let's spend another maybe about 10 minutes discussing about the meeting. If there are feedbacks on how to improve the format or any suggestions about it, please feel free to sort of discuss it now. So the floor is open for everyone to make suggestions.
So So Anamitra, I mean, one thing that is probably not manageable is having some theory and experimental sort of a collage, I mean, which probably has a very large number of people then, because condensed matter without experiments is a bit.
Yeah, I mean, okay, before I get into it, I should, just make one comment which I forgot to mention. I mean, I have been sort of handling the thing, but I just want to, make it absolutely clear that Ashish, Kush and Ravi have been integral part of managing the conference and helping us. They're sitting next to me, but I mean, I can show their faces to you, but yeah, thanks everyone. And of course, the sort of the national organizing committee at the moment, which were Shaurin, Manoranjan, Kalpataru, and Origin. So thanks everyone for helping us in sort of making the event a possibility. So let's come back to what Shubhro is suggesting. So Shubhro, I think this suggestion was also discussed last time. I think, as you say, I mean, the community is very big. I mean, once you bring in experimentalists, and already QMAT as a format exists for theory experiment. Now, you could make a case that if this is a meeting with younger people, in the sense of people who are coming back to the country, so are experimentalists and they should be included. I mean, I personally feel that is a good suggestion, except that then it becomes a very big meeting. That is, I mean, if it can be managed by all means, but generally that was not done, and we have been keeping with the tradition. I mean, I personally don't have anything against it, neither I think anybody has. So if there are other suggestions to that or comments,
no, so then maybe you can, sort of alternate speakers and phase out speakers, and then we can all listen to the talks, but maybe newer people may get a chance to speak.
No, we already did. So I mean, there are sort of a lot of good speakers that we have sort of, who have just been session chairs here, and I mean, and although they were not giving talks, Amit, Ghoshal, Sanjeev, Kalpataru, all these people, Manoranjan, all these people sort of gradually have sort of moved to more sort of a seniorish role, if you will. Yeah, but I don't know. I mean, getting experimentalists, I personally am not averse to it, except that this meeting is supposed to be a forum for theorists, and that's what we have been doing. If there are other suggestions, please, suggestions to this end, that if there is a way to bring in experimentalists,
no,
anybody has
I don't think so, because the philosophy of the meeting was that to give opportunity to the younger people who has come back to India. As you say, I completely agree. So if you make experimentalist also want to available, it will be very big. So yeah. And also it will bring more complexity.
Yeah, and Arijit, I mean, this was discussed many times.
Yeah, absolutely.
And we all decided finally that let's stick with the theory, because just for theory almost there is no other conference, but for experimental there are many conferences which happens all around the country, and there most of the time theoretical people are ignored. So that's the reason why it was started. Actually, many people suggested that you should stick with even senior people said that you stick with the theory. So that's the reason we have stick around, and we'll see in the future if we are able to manage later on.
Next year probably some of us can switch off from the talk, and we'll give chance to more younger people, those who have come back in last 1 year.
Yeah, sure, of course. Okay. So next year, hopefully, if the sort of COVID doesn't return, we would like to. I mean, we committed for 3 years at least, so we'll do it once, hopefully, in a physical a physical meeting. So we'll try to get everyone here. So that
would be really nice, because we are sick and tired of online.
Yeah, I mean, since I think the COVID and our taking over this meeting coincided, and so we could not invite people over. But at least before we sort of do it for the third time, we'll try to involve everyone.
Yeah. And one more request, I think, from the organizing committee we should have is, like, we should ask people to suggest the younger people. In many cases, we somehow miss some of the younger colleagues we joined.
So Manoranjan, so actually I think, so hi, this is Arnab here. So
yeah, Arnab, please go ahead.
Yeah, that's a good point, because I think this year, even in QMAT, and I think even last year, the organizers specifically asked many people to suggest younger people who have just come in, and maybe one can do it in this conference as well, right? So
sure,
yeah,
completely agree.
Yeah, that's actually one of a nice suggestion. Yeah, at the moment we were kind of looking on the internet to find out which institute has which people. That's the way we did it, to be frank. But it is true that, if we make some people who have already been in the meeting involved in this process as contact people who can just inform us, just like the QMAT people have asked for suggestions. I think that's something we can do in future, sure.
Yeah, and also I want to mention that in 2016 we started with 16 speakers. Now it is 38 in 2021, and the quality of the talk this time is really very good. And, also from India, the kind of work all younger people are doing really good. And I think in next 5 years the quality will jump to a much higher level.
Yeah, quality is of course good. I think the breadth of the work, in my view, has increased. Earlier, when we were students, certainly the fields were very sort of traditional, condensed matter, absolutely. X, Y, and Z, three or four broad areas. Now it's kind of a lot broader, and I think this meeting that's why makes a lot more sense. Because it sort of introduces people who have been in the country, the new things that people are doing, and gives a chance to interact. Of course, physically the meeting happens, the interactions become much more meaningful. You can actually catch up with somebody and talk.
Yeah. And because in the physical meeting, poster session will be more interactive. Because this year we experienced that.
That reminds me. So, did any of you guys? Also the students. Is there a particular feedback about the poster session? My personal thing was not very ideal, but please go ahead. Okay.
This is Subro. So my students said that there was a lot of interference within. There was rooms, right? So a lot of interference between what people were talking at different posters. So that
we
was
noticed
one
that. Yes.
that we faced, I think.
Yes. Yeah, they see this software is a bit complicated in the sense they use something called spatial audio, but it should not be very hard for them. So, if you have a postal location and you physically move away from there, the audio is supposed to drop in some power law, I guess, except that it did not drop off very well. We tried to... Yeah, I know they tried to they have this thing called sound zone or something, which makes it even more localized. But in our experience, it didn't work very well. Hopefully next year we don't have to deal with such things because we'll have the meeting physically. So we understand this poster session wasn't ideal. This particular the noise issue did create a problem.
So Ashish, do you remember what they used during this DD's conference? There was a poster session there too. I think that probably worked a little better during DD's 65th conference, this birthday conference.
I think it was,
there was a poster session there.
It was Gather.
I think it depends on what sort of platform is being used. Give it a try. If there are better platforms and if you are forced to remain in an online format next year too, then we'll certainly get in touch with you to know what the platform was so that we can take it up.
But hopefully it will be a physical conference next time.
Hopefully, yeah. We are certainly hoping that it will be a physical conference.
Yeah. One more suggestion I think I should point out here is, like, this meeting, the number of women speakers are less. That we should try to somehow enhance. That even
but see, I mean, I think that I agree. I mean, that I think what Arnab suggested perhaps will help, that if we are in case missing some people, you know,
that's correct.
So that it just helps us to get a better representation of women in science, which of course is very, very, very less at the moment, to be honest, among theorists in the country. So
that's correct.
Yeah, so yeah, that point we need to address at some level. I mean, I don't know, it's not easy to address. I mean, if the fraction of women by itself is less, then, you know, but we should make sure that we sample the full.
Yeah, that's right. I mean,
we
know that in physics the situation is quite worse, but like we should try to optimize as much as possible.
Yeah, exactly.
Because many times we got the complaint from the various agencies that, you know, even last year.
Oh, you got it.
Yeah. Last year, when I was doing, somehow we managed to have a good number and they appreciated it. Many people wrote that you guys have done the best in this video, but this should be promoted more and more.
Sure. So, any other suggestion? Anyone? Is the duration? Yeah, go ahead.
The duration is fine, I think.
Duration is fine.
Yeah, 4 days. And next year, probably, if we seem that it can be done possibly physically, then probably we'll start by sending invitation by June. If we want to arrange it in
yes, so that is true. I mean, with this COVID, etc., you know, things got a bit delayed. And last year, if you remember, we had the meeting in December. But this time, I think both the QMAT and this DA symposium covers that entire 10 days time. So that was not available. And I think after 20th December is not a good time to do because, you know, people will travel, etc. Anyway.
No, timing is very good actually. Even this year, it's very good.
Yeah, it's a very good time this year.
Yeah, this time is fine. A little bit of although.
So another thing, maybe we can go for next year hybrid mode if possible, because then we can have a significant number of postdocs who are doing research in outside India.
Yeah,
they can participate in the.
I mean, one good thing this time was that if you look at the postdoc participation, well, it's both good and bad in the sense that most of the postdoc participants were from abroad. But the bad thing is we also didn't have too many postdocs from India, which we ideally should have been able to accommodate. I mean, I don't think it's a problem if we, you know, make it a 4-day conference. I mean, if people are coming, then the 4th day, we are sort of ending it 3.5 days. So another half day would allow us to accommodate another maybe 7-8 postdocs.
Yeah.
So that should certainly be possible.
So if it's hybrid mode, then we can accommodate many, I think, who are.
Yeah, but then it's a question of time also. If we get too many.
No, so we can make too many, but it's like an application based that is shortlisting and then put it there.
Okay, sure. So. Yeah, sure,
because if we have a, if we are going to have a physical meeting, then I think it's better if we have it during, you know, like early January or sometime in towards mid-December.
Yeah, so that we have to figure out. Yeah,
we have a lot of teaching load, so it's difficult to travel in between a semester. And especially November, it's end semesters almost.
No, I think this, I mean, of course, we have to sort of, you know, once we have our timetables, etc., we can sort of fine tune it. But I think October-ish perhaps is because see, once the year, so it's happened now in November, so we cannot have it in January, right? It's too short a notice, so it pushes it back. So summer is a good time if that's something people are interested.
But Bhubaneswar is very hot in summer.
Yeah, that is true. No, but say if you do it before mid-December, around between 10th and 15th, is that a good time?
See, I mean, this, I agree with you, Shubhro, because, you know, even during all of us had to miss few talks because we were teaching parallelly. We had to manage and then go
this is
each class
online,
and come back.
manageable, but traveling is a...
No,
This is
that's
still
true. But
online,
I'm
so
saying
it's
that
fine.
this time anyway is not a very conducive time. December, as I said, I mean, the QMAT organizers sort of informed us, thankfully, early on that they are planning it in December. So last time it was in December. So that's why we were sort of kind of pushed it back. But I mean, I don't know. I mean, so I mean, and unfortunately, the DA symposium is also happening during that bit of time.
Maybe beginning of January or this.
So beginning of January,
which would
mean
the same time.
Yeah, because beginning of January means next year we cannot have it. Because
next year,
so that's an issue. I don't think we should give a gap. But again, that is my opinion. If people have suggestions, please go ahead.
Hi, this is Shubhro. I mean, one thing regarding this conflict with teaching, etc., is that there is a statistical physics community meeting that Abhishek, etc., organizes in ICTS, and what they try to do to accommodate to resolve this conflict partially is to include the weekend for the meeting, which particularly makes sense for physical meetings. So they start on a Thursday and then go over the weekend, so that sort of resolves partially the conflict. So that's one thing.
That is a good idea.
It's a good idea.
This is possible.
That's a good idea, and one can perhaps look for a weekend which is a long weekend,
even that. Yeah, that would be one thing, and particularly for physical meetings, that would also be a very nice. So that's one suggestion that might help.
Sure. Yeah, it's a good suggestion. Yeah, I think next time we can try to.
Yes. Okay, so I mean, are there any more suggestions from anybody or any comments?
Maybe next time. Sorry? Next time. The next time we are doing here, so maybe next time.
So so then should we close for this year? So okay, sure.
Thank you very much.
Then,
Thank you.
I would like
to thank all the organizers.
Local organizers there.
Yeah.
Thank you.
Very good. Very
guys.
nice.
Okay. Thanks,
We'll
guys.
see you
Thanks to
next
all
year.
the organizers. Yeah.
Cheers to all of the coach.
Thank you.
So they are thanking you guys also. You guys, they are behind the laptop. Sorry. All right, guys.